The ocean spreads across more than 70% of Earth's surface. Yet when you really think about it, less than 5% of it has been carefully mapped. Everything else remains an enormous unknown, a true blank on our maps, unseen and untouched, despite satellites circling far above us, and despite the most sophisticated sonar systems and robotic machines we have ever built. Vast regions beneath the waves are still wrapped in mystery. In fact, we understand the surface of Mars in greater detail than we understand the floor of our own oceans. And to give that some context, only 3 human beings have ever descended to the Challenger Deep, the deepest point on our planet. That is fewer people than have set foot on the moon. Down there, familiar rules no longer apply. At around 1,000 meters, the final traces of sunlight disappear completely, never to return. Beyond that depth, there is a darkness so absolute it has existed for millions of years without interruption. And yet, against all intuition, life not only exists there, it flourishes. There are organisms so unusual they challenge nearly everything we once assumed about how life must function. Entire communities survive not by sunlight, but by the heat and chemicals released from volcanic vents on the seafloor. With every descent into these depths, scientists come back with living forms we had never imagined, creatures no one had ever documented before. The ocean carries secrets that constantly remind us just how limited our knowledge of our own planet really is. Most of it remains undiscovered, quietly waiting, and the unsettling reality is that we may never fully explore it all. Not because we lack wonder or curiosity, but because the obstacles are so immense. So what truly prevents us from exploring the ocean the way we imagine? What stands in our way, even in an era when we can build rockets, leave Earth, and send machines to distant worlds? And why does the sea, right here at home, remain humanity's greatest unknown? Tonight, we'll journey together into the ocean's dark side, to understand what we know, what we still don't, and why some secrets of the sea may always stay just beyond our grasp. But before we go any further, I'd genuinely love to know where you're listening from and what time it is where you are. It's always remarkable to think of these stories traveling across so many different skies. If you enjoy these calm explorations into Earth's mysteries, please consider leaving a like and subscribing to the channel. And a heartfelt thank you to those of you who are already subscribed. You're helping this small corner of the internet continue to grow. I truly hope this story gently guides you toward rest. So take a slow, deep breath, let your shoulders relax, close your eyes if you wish, and let's begin. When we lift our eyes to the night sky, the stars seem unimaginably distant, and yet they carry a sense of familiarity. With the help of telescopes, we observe the dim light of galaxies that sit billions of light years away. We can follow the shapes of glowing nebulae and calculate the sizes of planets circling stars far beyond our own Sunday. Space feels immense, but it also feels accessible, as though its secrets are laid out before us, waiting to be uncovered one by one. What is truly remarkable, however, is that our ability to examine these faraway realms often exceeds our ability to understand what exists beneath the surface of our own oceans. The explanation begins with the fundamental properties of light and water. Satellites traveling high above Earth can transmit radar signals across continents and deserts, charting mountain ranges and river systems with extraordinary precision. They can record the craters of the Moon and the vast canyons of Mars in striking detail. But when those same signals encounter the ocean, they fail to travel very far. Water absorbs light, bends radio waves, and scatters sound, turning the ocean into a shimmering barrier that conceals everything below. What satellites can reliably measure is the surface of the sea itself. In certain regions, slight bulges and depressions in the water hint at the presence of ridges and trenches hidden far beneath. These gravity-driven signals provide us with an approximate outline of the seafloor, a broad sketch rather than a detailed portrait. This is how we know the general form of the Mariana Trench or the Mid-Atlantic Ridge, but the image remains soft and unclear, like viewing the shadow of a mountain instead of the mountain itself. When astronomers rely on space-based telescopes, they are looking across distances so vast that the numbers feel almost unreal. Light that has traveled for billions of years still reaches our instruments. We are able to chart the structure of the universe across time, capturing images of galaxies as they appeared when Earth itself was young. By contrast, when oceanographers attempt to chart the deep sea, they encounter limitations within just a few kilometers. Underwater, sound replaces light as the primary tool. Sonar systems emit pulses that reflect off the seabed, and by timing how long the echoes take to return, scientists can estimate depth and shape. Yet the ocean is enormous, and sonar mapping must be carried out slowly, vessel by vessel, across immense areas. Even then, sound weakens as it travels, and the deeper the water becomes, the more difficult it is to detect what lies below. The result is a collection of partial maps, narrow bands of clarity pieced together over many years, while most of the ocean floor remains unknown. Now consider Mars, a world tens of millions of kilometers away. From orbiting spacecraft, we possess high-resolution images of its surface. We can identify ancient river channels, measure the heights of long-dormant volcanoes, and observe dust storms sweeping across its plains. Mars is dry, lifeless, and distant, yet we understand it more thoroughly than the dynamic oceans of our own planet. Earth's seafloor, by comparison, is unevenly charted and incomplete, like a canvas left mostly empty with only a few painted lines. This contradiction lies at the core of the issue. Outer space, though far beyond ordinary reach, is transparent to our instruments. The ocean, though it surrounds us and covers most of the planet, remains stubbornly opaque. The technologies that perform so well in studying the cosmos struggle against the density and depth of water. Each advancement we make reveals not only how far we have come, but also how much remains unexplored. Time itself adds another layer to the challenge. A spacecraft orbiting a distant planet can collect enormous amounts of data in a single pass, surveying vast regions in a matter of days. Mapping the seabed with sonar, by contrast, is like using a fine brush to paint a canvas the size of Earth. It requires not days but decades. And even then, most of the picture remains empty. And so we find ourselves in an unusual position. We have charted the red landscapes of Mars in sharp detail, yet we cannot confidently describe what lies beneath the waves along our own shores. We can observe galaxies so ancient that their light began its journey before life emerged on Earth, but we cannot say with certainty what creatures inhabit the depths just a few kilometers below us. It is this stark contrast that deepens the mystery of the ocean. The universe offers us a view, however distant, while the sea keeps its secrets close. What we possess are brief glimpses, outlines, and fragments, hints of terrains and living forms that remain hidden from sight. And as we move beyond the question of what we can see and turn toward the deeper reality of the ocean itself, we are forced to face obstacles that exist not only because of the limits of our tools, but because of the deep ocean's very nature. Beyond the challenge of mapping lies something far more demanding: the abyss, defined by overwhelming pressure, relentless cold, and permanent darkness. The farther we descend beneath the surface, the more the familiar rules of our everyday world begin to fall apart. What appears calm and gentle at the surface conceals conditions so extreme that they push human engineering and human imagination to their breaking point. With every meter downward, another layer of difficulty is added, until the ocean is no longer simply water, but a vast stronghold guarded by pressure, cold, and darkness. The first of these obstacles is pressure, an unseen force that grows heavier with every step into the deep. At the surface, we live under the mild weight of one atmosphere, the pressure of the air above us. But for every 10 meters of depth, the ocean adds another full atmosphere of force. By the time a depth of 1,000 meters is reached, the body is already enduring 100 times the pressure experienced on land. To go deeper still is to confront forces so powerful they can crush steel and shatter glass. This is why deep-sea submersibles bear little resemblance to the sleek vehicles of fiction. They are not streamlined, but spherical, because a sphere spreads pressure evenly across its surface. Their walls are thicker than bank vaults, built from multiple layers of steel and titanium. Even with such designs, every dive remains dangerous, because a single flaw or tiny crack can lead to catastrophe. The Trieste, the first vessel to reach the Challenger deep in 1960, experienced a cracked window during its descent, a stark reminder that even the strongest human creations are fragile when faced with the weight of the deep. Pressure does not only challenge our machines, it reshapes life itself. Creatures living in the abyss have cell membranes strengthened by specialized proteins and enzymes that allow them to endure immense force. Their bodies often lack air-filled spaces that could collapse under pressure. For them, pressure is not a threat, but a constant, the normal condition of existence. For us, it remains an almost impassable barrier, separating our world from theirs. Cold forms the second barrier, creeping in long before the deepest trenches are ever reached. Even at moderate depths, beyond the reach of sunlight, water temperatures drop quickly. Within a few hundred meters, the warmth of the surface gives way to a near-freezing chill. In the deep ocean, the average temperature stays just above 0 degrees Celsius. It is a cold so constant and unchanging that it has shaped entire ecosystems. For humans, such conditions can lead to hypothermia in minutes. For machines, the cold slows electronics, thickens lubricants, and makes moving parts brittle and unreliable. Life in these depths has adapted in remarkable ways. Many deep-sea animals operate with extremely slow metabolisms, conserving precious energy in the cold. Some produce antifreeze-like proteins that stop ice crystals from forming in their blood. Fish and invertebrates often move with deliberate slowness, relying on efficiency and patience rather than speed. The cold preserves the deep ocean like a natural archive, allowing shipwrecks and animal remains to stay intact for centuries. For explorers, however, this means every mission must include heating systems and heavy insulation just to keep equipment functioning in the face of the silent freeze. Then there is the barrier that defines the abyss more than any other: darkness. Sunlight, the great driver of life, disappears quickly in water. At a few hundred meters, only a faint blue glow remains. By 1,000 meters, the final ray of sunlight is gone forever. Beyond this twilight zone stretches a permanent night that no human eye has ever fully adapted to. Here, the only light comes from living organisms themselves, brief flashes of bioluminescence pulsing through the black, or the short sweep of a remotely operated vehicle's lamp moving across the seafloor. This darkness is more than the absence of light. It is an environment where evolution has taken unusual paths. Many deep-sea creatures possess eyes that are enormous in proportion to their bodies, built to capture the smallest glimmer. Others have lost their eyes entirely, evolving instead to sense vibrations or chemical signals in the water. For humans, darkness removes all natural reference points, leaving even the most advanced submersibles reliant on instruments rather than sight. In these depths, the ocean floor is revealed only by sonar echoes and the dim reach of artificial lights, never by natural vision. To confront pressure, cold, and darkness all at once demands an extraordinary level of engineering, one that often seems close to impossible. Every descent into the deep requires not only a vessel capable of surviving crushing pressure, but also systems that can function in freezing temperatures and navigate a world where light does not exist. Even so, the ocean continues to push back against us. Expeditions into its depths are uncommon, expensive, and fleeting. For the most part, the abyss remains largely untouched, standing as a reminder that the sea does not surrender its secrets easily. And yet, it is these very limits that give the deep ocean its powerful sense of mystery. Each attempt to descend further reminds us not only of how unforgiving this environment is, but also of how remarkably life has already adapted to survive there. For every barrier that appears impossible for us to overcome, there are creatures that have found ways to flourish, transforming the abyss into their natural home. As the story of the ocean continues to unfold, a lingering question remains: what kinds of landscapes are hidden in these depths? The immense scars and trenches of Earth that humans have reached only a handful of times. Far below the restless surface waves, beyond the reach of sunlight and warmth, the seafloor drops away into enormous chasms carved deep into the planet's crust. These are the deep ocean trenches, among the most extreme and least explored environments on Earth. They are the marks left by tectonic forces, formed where one plate of Earth's crust slides beneath another, forcing solid rock downward toward the mantle. The result is a vast wound in the planet's surface, stretching for hundreds of kilometers and plunging to depths greater than the height of mountains. The most well-known of these is the Mariana Trench, resting quietly in the Pacific Ocean. At its deepest point, known as the Challenger Deep, the seabed descends nearly 11 kilometers below the surface. To imagine such a depth, picture Mount Everest, the tallest mountain on Earth, turned upside down and placed inside the trench. Even then, its peak would still be buried beneath more than 2 kilometers of water. It is a place so distant and so hostile that only a few humans have ever witnessed it with their own eyes. The first journey came in 1960, when the bathyscaphe Trieste carried Jacques Piccard and Don Walsh down into the darkness. Their descent took nearly 5 hours as the small vessel groaned under immense pressure. When they finally reached the bottom, they saw a flat expanse of silt, disturbed by their landing. Through a small porthole, they reported observing signs of life, even at that depth, small creatures moving through the gloom. After only 20 minutes on the sea floor, they began the long ascent back to the surface, leaving the trench much as they had found it. More than 50 years would pass before another human returned. In 2012, filmmaker James Cameron made a solo descent in a custom-built submersible. His craft, the Deep Sea Challenger, was tall and narrow, engineered to endure the crushing pressures of the trench. He spent hours exploring, collecting images and samples that revealed a stark, yet hauntingly beautiful environment. Still, his dive, like those before it, covered only a minute portion of the trench, little more than a single point in an immense abyss. Since then, only a small number of additional dives have taken place, often using experimental vehicles or privately funded missions. Even now, the total number of people who have visited the Challenger Deep remains fewer than those who have walked on the moon. Every descent represents a triumph of engineering, requiring vessels with walls thicker than vault doors, systems capable of surviving freezing temperatures, and instruments designed to operate in complete darkness. Yet, the Mariana Trench is just one example. There are more than 20 known deep-sea trenches across the globe, from the Tonga Trench in the South Pacific to the Puerto Rico Trench in the Atlantic. Many of these reach depths close to that of the Mariana, and yet most are still unmapped and unexplored. They are enormous gashes in Earth's surface, concealed beneath miles of water, containing landscapes as dramatic as the tallest mountain ranges. Steep cliffs, twisting valleys, and towering geological structures lie hidden there, unseen and untouched. What little we know about these trenches often comes not from direct human observation, but from distant measurements. Deep-towed sonar has hinted at strange shapes, while robotic submersibles have captured brief images of unfamiliar life drifting through the darkness. Amphipods, as large as human hands, translucent snailfish, and microbial mats clinging to rocky walls have all been discovered in these depths. Yet, each expedition seems to raise more questions than it answers. The scale of what remains unknown is immense, as though we are peering through a door that has been opened only a tiny crack. These trenches are not just biological frontiers, but geological ones as well. They mark the boundaries of tectonic plates, where Earth quietly reshapes itself over time. Earthquakes often ripple along these edges, and tsunamis are born in their shadows. Entire mountain ranges rise and fall because of the slow, relentless movement at these boundaries. And still, we lack detailed maps of these regions and a clear understanding of their hidden structures. For the moment, these places exist almost like distant whispers, locations that feel as much a part of science fiction as they do of real science. And so, despite the ocean encircling our world, the reality is that its deepest regions remain out of our reach. We have done little more than graze the upper edges of these vast chasms, brushing against their margins while their enormous interiors stay hidden in shadow. Year after year, our tools and machines grow more advanced, but the trenches continue to remind us of how much we do not know, and how small and vulnerable our efforts are when faced with the immense pressure of the sea. As we move further into this story, the lingering question is not just what these enormous scars in Earth's crust look like, but what kinds of life exist within them. Because in these lightless corners of the planet, living things have somehow managed to persist against incredible odds, surviving in environments that seem completely unlivable, and it is toward these delicate and remarkable forms of life that our focus now turns. For as long as humans have traveled across the oceans, there have been murmurs of strange creatures emerging from the depths. Sailors spoke of enormous tentacles, as thick as tree trunks, coiling around ships and dragging them down into the dark waters below. For centuries, such stories occupied the space between terror and imagination, often dismissed as pure fantasy. And yet, in recent decades, we have discovered that reality was closer to legend than we once believed. The giant squid, once confined to the realm of maritime myth, has been proven to exist not as a tale, but as a living animal, with bodies extending over 12 meters and eyes larger than a human head. These creatures serve as a powerful reminder that the ocean has always guarded its secrets carefully. For most of human history, no one observed them alive. What knowledge we had came from bodies washed onto beaches or pieces, caught accidentally in fishing nets. It was only in the early 21st century that cameras finally recorded a giant squid in its natural environment, moving quietly through the dark, midnight waters. Even today, much of its life remains unknown, its habits concealed in the depths, and the giant squid is only one example. The deeper one descends, the more unfamiliar the ocean becomes, as if each level is an entirely different world. In the abyss, where sunlight has never penetrated, organisms have been forced to evolve in ways that challenge our assumptions. Their bodies are shaped by crushing pressure, intense cold, and endless darkness. Many are nearly transparent, their ghost-like forms blending seamlessly into the surrounding water. Some species have developed the ability to generate their own light, turning themselves into living beacons used to attract prey, signal to partners, or confuse attackers. Others are slow-moving scavengers, carefully conserving energy in a place where food is rare, where the slow descent of a whale's body from the surface can sustain whole communities for decades. Each expedition into these depths brings new revelations. Remote-operated vehicles, or ROVs, have given us far more access to the abyss than humans could ever achieve themselves. Equipped with cameras, mechanical arms, and powerful lights, these machines sink into regions where pressure would easily destroy steel and where cold would halt most forms of life. And every time they descend, they return with images of creatures never documented before. Scientists estimate that most deep-sea species have yet to be discovered, their shapes still concealed within trench walls and cracks along underwater mountain ranges. It is as though the ocean is a book we have barely begun to read, with each page offering another surprise. Some of these findings are both mesmerizing and unsettling. Jellyfish with trailing filaments stretching dozens of meters drift like galaxies beneath the waves. Fish with transparent heads and eyes, positioned to look upward through their skulls, monitor the faintest traces of light above. Shrimp covered in glowing patterns move together in synchronized displays, resembling living constellations. And yet, for every unusual organism we briefly observe, countless others slip back into darkness before we can learn anything about them. The difficulty of studying these beings means we often possess only fragments of their stories. A fish captured on camera for a few seconds may never be seen again. A specimen brought up from the depths may not survive long enough for us to understand how it lives. Entire ecosystems flourish under conditions that feel utterly alien to us. And the more we uncover, the more questions seem to multiply. How do these creatures reproduce in complete darkness? How do they move and orient themselves in a silent world without landmarks or light? And perhaps most puzzling of all, how many of them exist in areas of the ocean that no machine has ever reached? It is humbling to recognize that even in an era of satellites and global communication, the largest habitat on Earth remains largely unexplored, a frontier still touched by myth. The ocean has nurtured millions of years of evolution, shaping bodies and behaviors never witnessed by human eyes. Somewhere within the black passageways of trenches and across the wide plains of the abyss, there are forms of life so strange they may force us to rethink what life itself can be. Every ROV descent, every brief window into the unknown, reminds us that our planet has not been completely charted, not fully classified, and not entirely understood. As we continue moving deeper, it becomes increasingly clear that the noises, images, and signals of the deep ocean are just as mysterious as the life forms that inhabit it. The sea is far from quiet, and what we have detected from its depths can be just as unsettling as the strange beings drifting through the darkness. The ocean is often described as silent, but in reality, it is anything but. Beneath the surface, sound becomes the dominant presence. Crashing waves, the songs of whales, snapping shrimp, and currents surging across the seafloor all blend together into a concealed symphony that fills the dark waters. Unlike light, which disappears after only a few hundred meters, sound moves through water with remarkable efficiency. Low-frequency sounds can travel vast distances, crossing entire oceans, as they pass through what scientists refer to as the sound channel, a deep layer where sound waves can move for thousands of kilometers with very little loss of strength. Within this hidden acoustic pathway, some of the most puzzling signals ever documented have been detected. One of the most well-known is simply called the bloop. It was recorded during the summer of 1997 by hydrophones, originally deployed across the Pacific Ocean during the Cold War to detect submarines. The sound defied expectations. Its pitch rose in a way that resembled the call of a living organism, and it was so powerful that sensors located more than 5,000 kilometers apart all registered it. At the time, no known animal could account for such a signal. Even blue whales, the loudest animals on Earth, do not produce sounds at that pitch, and the sheer intensity of the bloop seemed beyond the capability of any known creature. For years, the mystery persisted, fueling speculation that enormous, unknown beings might exist in the deep, unlike anything ever observed. Later, many scientists proposed that the sound may have originated from massive icebergs fracturing and shifting, but the legend of the bloop endures because in the ocean, the boundary between explanation and mystery is rarely clear. Not long after, another unusual signal received a name. It was called Julia, a prolonged, mournful sound recorded in 1999. The signal lasted for nearly 15 seconds, resonating across the Pacific. Some researchers suggested it was also caused by ice breaking apart, yet others could not dismiss the unsettling sense that it resembled a cry, as if the ocean itself had exhaled a deep sigh. What made Julia so striking was not just its haunting quality, but the reminder that water, with its extraordinary ability to transmit sound, can easily conceal the true origin of a signal. Julia, much like the bloop, left behind more questions than answers. Then there was upsweep, the name given to a recurring pattern of sounds first detected in 1991. Upsweep is made up of long, rising tones, almost as though produced by some unknown instrument. It has been recorded seasonally ever since, most often strongest in spring and autumn, yet its source remains unidentified. The regularity of its pattern suggests it is unlikely to be random noise. Some scientists have suggested volcanic activity, as the region where it was detected lies along the fault lines of the Pacific. Some researchers lean toward biological explanations, suggesting unknown life rhythms that we have not yet identified. Upsweep, in particular, continues to confound scientists, a signal with no clearly identified source. Beyond it, there are many more sounds scattered throughout decades of monitoring: whistles, groans, bangs, and low hums that suddenly appear in hydrophone recordings and then disappear just as abruptly. A number of these noises have eventually been linked to natural causes such as undersea earthquakes, shifting ice masses, or the movement of powerful storms. Yet many others remain unexplained, echoing from depths where crushing pressure dominates and sunlight never penetrates. In these regions, sound becomes the only witness, carrying traces of events and possibly living beings we cannot see. These ghostly sounds serve as a reminder of how limited our understanding of the ocean's interior truly is. They also highlight how dominant sound is beneath the waves. On land, light shapes how we perceive distance and space, but in the ocean, It is vibration, echo, and resonance that define the environment. Whales rely on sound to locate one another across entire ocean basins. Submarines once depended on it for concealment and survival. And hydrophones, originally installed to monitor potential conflict, have instead opened a window into mysteries no one expected to encounter. Every unexplained signal carries a sense of wonder, because in a realm as vast and hidden as the sea, any sound could belong to something entirely unfamiliar. The bloop, Julia, upsweep, and countless others are more than noises in the dark. They are reminders that the ocean is filled with voices, some we recognize, and others that may always remain beyond our understanding. And as hydrophones continue to listen, the sea keeps whispering its secrets, drawing us further into its story, where each descent promises the possibility of new discovery. In the deepest parts of the ocean, where sunlight disappeared long ago and darkness seems endless, there is still light generated by life itself. It appears in soft pulses, sudden flashes, and flowing waves, moving across the bodies of creatures that seem almost otherworldly. This is bioluminescence, a phenomenon both widespread and deeply mysterious, one that scientists are only beginning to grasp in its full complexity. Bioluminescence is far from rare in the ocean. In fact, most deep-sea animals are believed to possess some form of it. The light is produced by a chemical reaction inside the organism, where a molecule known as luciferin reacts with oxygen, often activated by an enzyme called luciferase. This reaction releases energy as light, typically glowing in shades of blue and green that travel efficiently through seawater. To human observers, the sight can feel magical, but it is entirely natural, refined by evolution over millions of years. The purposes of this living light are as diverse as the creatures that produce it. Some use it as a hunting tool. The anglerfish, suspended in the blackness, waves a glowing lure just in front of its mouth. Curious or deceived prey drift closer to the light, unaware until the predator closes its jaws. Other animals use bioluminescence defensively. When threatened, certain squid release clouds of glowing ink that confuse attackers and allow time to escape. Some fish emit sudden bursts of light that startle predators into retreat. Even microscopic plankton can glow when disturbed, creating waves of light so bright they are visible from space, transforming entire regions of ocean into shimmering blue fields. Communication is another hidden role of light in the deep. In a place where vision is limited, some species use bioluminescence as a language. Flashing patterns can signal readiness to mate, mark territory, or help individuals recognize others of their own kind. Some deep-sea shrimp release brief, coated bursts of light, while lanternfish display glowing patches on their bodies like identification markers. Each flash and shimmer carries meaning in the silent darkness. Perhaps the most haunting displays are those that appear almost artistic. Entire schools of fish move together, their lights rippling like shifting constellations beneath the surface. Comb jellies, delicate and glass-like, scatter rainbows of iridescence as they drift. At times, a single organism can resemble a floating galaxy, streaked with sparks of blue or green flowing along its transparent body. These scenes remind us how alien the deep ocean can feel, even though it belongs to our own world. What stands out most is how much remains unknown. For many species, the exact reasons behind their glow are still uncertain. Why would a tiny worm emit bright red light in an environment where red wavelengths disappear almost instantly? Why do some jellyfish flash in patterns so intricate they seem deliberately designed? Every answer leads to new questions, and every expedition returns with unfamiliar examples of life, illuminating the darkness in unexpected ways. The adaptability of bioluminescence is equally striking. It appears across an enormous range of life, from microscopic bacteria to massive squid. This suggests that the ability to produce light has evolved independently many times, each instance serving as a solution to the challenge of surviving in perpetual darkness. It is not the result of a single invention, but of countless solutions, each shaped by its surroundings, each offering a different way to survive in the deep. The marvel of this light is not limited to the most extreme depths. Even close to shore, on warm nights, Swimmers can sometimes see glowing trails forming around their hands and feet as tiny plankton react to movement. Waves crash against the beach in lines of pale blue fire, and the tracks left by crabs shimmer faintly across the sand. These modest displays are reflections of a far greater spectacle hidden below, gentle reminders that the ocean holds far more mysteries than our eyes can perceive. To realize that, in the complete absence of sunlight, life has created its own version of daylight, its own lamps in the darkness, is both deeply humbling and profoundly astonishing. Bioluminescence transforms the deepest parts of the ocean into a constantly shifting, glowing stage where survival, signaling, and even beauty unfold in complete silence. And as we move further into this narrative, it becomes apparent that even more unusual layers of the sea are waiting for us, places where day and night no longer exist as we understand them, but merge into something else entirely. Between the bright, sunlit surface waters and the endless darkness of the deep lies a zone unlike any other on Earth. Scientists refer to it as the mesopelagic zone, though it is often more evocatively called the twilight zone. This region begins at roughly 200 meters beneath the surface and extends down to nearly 1,000. Here, light does not simply disappear, but fades gradually into a dim, ghost-like glow. Sunlight still reaches this depth, but only weakly, enough to blur shapes and shadows, never strong enough to support the green life of plants. It is a world suspended between day and night, a shifting boundary that shelters some of the most elusive organisms on the planet. The twilight zone spans an enormous area, wrapping around the Earth like a concealed band of mystery, completely unseen from above. Its scale is staggering, holding more living biomass than all of the world's rainforests put together. Within these dusky waters move vast numbers of fish, squid, jellyfish, and drifting plankton, many of which have never been fully observed or studied. Their bodies are perfectly adapted to the dimness. Some have smooth, silvery flanks that reflect the faint remaining light, allowing them to blend seamlessly into their surroundings. Others are almost pitch black, their forms dissolving into the darkness below. Many carry their own sources of light, tiny sparks of bioluminescence that pulse and shimmer like stars scattered across a fluid sky. Each evening, as the sun sinks and darkness spreads across the sea, the twilight zone erupts with the largest migration on Earth. Billions of fish and invertebrates rise from the depths toward the surface, a movement so vast it can be detected from space as shifting shadows beneath the waves. During daylight hours, they stay hidden far below, protected from predators. At night, they ascend to feed on plankton near the surface, their glowing bodies moving in harmony with the planet's daily rhythm. This journey, repeated over and over again, may involve more animals than all the herds and flocks on land combined. And yet, for most of human history, no one knew it was happening at all. Life in this zone is adapted to conditions that are both fragile and extreme. Many species possess enormous eyes, finely tuned to capture the faintest traces of light, often angled upward to detect the silhouettes of prey above them. Others rely on counter-illumination, producing light on their undersides to match the weak glow filtering down from above, effectively erasing their outlines from view. Some conserve energy by drifting slowly, moving as little as possible in waters where food can be scarce. And then there are those that hunt using light itself, flashing to lure prey closer or to confuse it just long enough to strike. Despite its richness, the twilight zone remains largely unexplored. It lies too deep for satellites to observe clearly, yet too shallow for most deep-sea submersibles to study for long periods. Nets hauled up from these depths often crush or destroy the fragile creatures they catch, leaving scientists with damaged remains instead of intact specimens. Cameras struggle as well, overwhelmed by pressure, cold, and darkness. What we know comes from brief encounters, short missions, and fleeting shadows detected by sonar. In reality, only a small portion of this immense environment has been examined. What little we have learned suggests that the twilight zone plays a vital role in maintaining the balance of our planet. As its inhabitants rise each night to feed, they transport carbon with them, carrying it from the surface back into the depths when they descend at dawn. This vertical movement, repeated every 24 hours by billions of animals, helps regulate Earth's climate. Yet the true scale of this process remains unclear, because the very creatures responsible for it are still, for the most part, unknown. To slip into the twilight zone is to step into a place that feels almost unreal, hovering between brightness and darkness, where the clear lines that define life at the surface begin to fade into shadow. It is a region overflowing with life, and yet it remains largely unseen, hidden just beyond the limits of human vision. As we move farther into the ocean's depths, we don't simply pass through layers of water, we uncover layers of living systems, each one more surprising than the one before it. In the late 1970s, a group of oceanographers sent a submersible down into the dark waters near the Galapagos Islands. Their goal was straightforward: to examine a stretch of seafloor along a mid-ocean ridge, a place where the Earth's crust is slowly tearing apart. There was no expectation of discovery. At the time, the deep ocean was believed to be lifeless, a barren wasteland where survival was impossible without sunlight. But in 1977, when the submersible's lights swept across the seafloor, everything scientists thought they knew was challenged. What appeared before them were hydrothermal vents, cracks in the Earth's crust where seawater sinks deep into the planet, heats up against hot rock, and then erupts back into the ocean, carrying dissolved minerals and chemicals from far below. These vents resembled chimneys rising from the seabed, some towering like underwater skyscrapers, releasing thick, dark plumes into the surrounding water, and clustered around them, to the scientists' amazement, was life. Not a few isolated organisms, but full, flourishing ecosystems gathered around these black smokers, glowing faintly in the beams of the submersible. Massive tubeworms formed dense clusters, their bright red plumes waving gently with the currents. Large clams, as wide as dinner plates, coated the rocks. Unusual crabs crawled over the vent openings, and fish slipped in and out of the shimmering, mineral-rich water. It was astonishing. A complete biological community existed there, entirely independent of sunlight. For all of Earth's history, it had been assumed that photosynthesis sat at the base of every food web, that without the sun no ecosystem could exist. Yet, here, in the immense pressure and total darkness of the deep ocean, life had discovered an alternative path. The key was chemistry. At these vents, bacteria used hydrogen sulfide, a substance poisonous to most animals, as their primary energy source. Instead of relying on light through photosynthesis, they carried out chemosynthesis, creating sugars and sustaining themselves using chemical energy alone. These bacteria formed the foundation of the vent ecosystem, nourishing tubeworms, clams, and many other species specially adapted to survive there. What had once been imagined as an empty desert turned out to be a place of extraordinary abundance, fueled entirely by heat from within the Earth. The discovery of hydrothermal vents opened deep questions about how life began. If living systems can thrive in such extreme darkness and pressure, conditions far beyond anything on the surface, then it is possible that Earth's earliest life emerged in similar environments. These vents offer both energy and protection, with mineral-rich chimneys creating small, sheltered spaces where molecules can collect and interact. Some scientists suggest that these vent systems may have been the birthplace of life itself, where simple chemical reactions gradually crossed the threshold into biological complexity and produced the first living cells. The implications reach even further. If Earth's oceans can support rich ecosystems without any sunlight, then perhaps the same could be true elsewhere. Moons such as Europa and Enceladus, orbiting far from the sun, are thought to conceal vast liquid oceans beneath thick layers of ice. If hydrothermal vents exist on their ocean floors, as many models indicate, then life may not be unique to Earth. Chemosynthesis could represent a universal strategy for survival in environments where light never penetrates. Each new journey to hydrothermal vent fields continues to reveal remarkable adaptations. Tubeworms, for instance, have no mouths and no digestive organs at all. Instead, they host symbiotic bacteria inside their bodies, allowing them to draw nourishment directly from chemosynthesis. Vent shrimp possess light-sensitive areas on their backs that may help them sense the faint glow of hot fluids in the darkness. Even the chimneys themselves, constructed from minerals brought up from beneath the crust, become delicate habitats, each one a temporary tower of stone and life rising from the abyss. Despite their richness, hydrothermal vents are extremely vulnerable. The very minerals that make them so distinctive have drawn human attention, especially from deep-sea mining interests. Metals such as copper, zinc, and even rare earth elements build up within the chimneys, tempting industries that view the deep ocean as the next resource frontier. But these ecosystems are fragile and short-lived, sometimes existing for only a few decades before shifting, weakening, or collapsing entirely. Disturbing these environments could wipe out entire communities we scarcely understand and species that remain undiscovered. What stands out most about hydrothermal vents is how powerfully they show that life is not confined to the limits we once believed were unbreakable. In the absence of sunlight, without plants, and without the familiar rhythms of land and air, living systems do more than persist, they thrive. These places remind us that the ocean's secrets are not just about bizarre creatures or unreachable depths, but about the deeper narrative of life itself. And as we sink further into that narrative, new layers of the ocean slowly reveal themselves, drawing us ever deeper into uncertainty. When we shift our gaze beyond Earth, past the swirling clouds and the blue arc of our seas, we encounter other worlds that initially appear lifeless. Icy, airless moons, orbiting giant planets seem frozen and inert. Yet beneath their solid shells of ice, scientists now suspect the presence of concealed oceans, immense bodies of liquid water locked away in darkness. Europa, Jupiter's luminous moon, is one such world. Its surface is crisscrossed with long fractures, shaped by tidal forces so intense they warm its interior. Below those cracks lies an ocean that could be more than 100 kilometers deep, holding more water than all of Earth's oceans put together. Enceladus, a much smaller moon of Saturn, provides equally compelling clues. In 2005, the Cassini spacecraft passed close by and detected geysers blasting out from its south pole, streams of water vapor and ice particles spraying into space. These jets originate from a global ocean beneath its crust, heated by tidal friction, and the water contains salts and simple organic molecules, signs that chemistry is actively unfolding in the darkness below. Then there is Titan, Saturn's largest moon, a world so unusual it blurs the line between the familiar and the truly alien. On Titan, rivers and lakes made of methane and ethane carve the surface, while beneath its icy exterior, scientists believe there is an ocean of water mixed with ammonia. What makes these findings so unsettling is how closely they mirror our own planet. Beneath immense pressure and complete darkness, hydrothermal vents on Earth release heat and minerals, creating environments where life prospers without sunlight. If similar conditions exist on Europa or Enceladus, they too could support ecosystems of their own. Chemosynthesis, the same process that sustains life around our vents, may be a universal solution. The design is already here, concealed within our oceans. But if the seas on our own planet are still largely unexplored, how can we expect to uncover what lies beneath the ice of faraway moons? On Earth, we have barely skimmed the edges of the abyss. Every descent reveals unfamiliar species, unseen landscapes, and new puzzles, even though the ocean surrounds us everywhere. Now consider the challenge of sending probes across hundreds of millions of kilometers, drilling through ice thicker than any glacier on Earth, and lowering instruments into oceans we cannot observe directly. The difficulty is immense, yet the possibility exerts a pull as strong as gravity itself. When scientists explore Earth's deep oceans, they are doing more than learning about our planet. They are preparing for voyages beyond it. Microbes that survive on chemicals instead of sunlight, translucent fish drifting through the twilight zone, and organisms that generate their own light all show us what life can become in worlds cut off from a star's warmth. Every mission to a hydrothermal vent or a polar sea offers a preview of conditions that might exist on Europa or Titan. Our oceans serve as a living laboratory, the only reference we have for imagining life elsewhere. These alien seas provoke questions that feel both scientific and profoundly human. Could life exist in places so distant from starlight? Would it resemble anything we recognize? Or take forms entirely unfamiliar? If one day we send a submarine beneath Europa's icy shell, will it glide past glowing clouds of plankton-like organisms, or encounter only bare rock shaped by silent currents? The answers remain hidden, waiting in waters that may have been undisturbed for billions of years. The ambition to reach these oceans represents exploration at its boldest. It demands that we travel not only farther than ever before, but deeper than we have ever managed. Before we break through the ice of distant moons, we must learn to read the secrets of our own seas, because here on Earth, the same story is unfolding quietly. What we uncover in our oceans does not belong solely to us. It may be the key to recognizing life when we finally encounter it beyond our world. In this way, the mysteries of the deep sea and the mysteries of the cosmos are inseparable, reflections of the same enduring question. What does it mean for a planet or a moon to be alive beneath its waves? Far below the reach of sunlight, the sea floor is anything but still. It is alive with heat and motion. In these regions, Earth's crust is thin, fractured, and restless, allowing energy from the mantle to escape. More volcanoes are hidden beneath the ocean than exist on all the continents combined, and some estimates suggest that 3/4 of Earth's volcanic activity takes place underwater, silent and unseen. These submarine volcanoes rise from the depths like mountains of molten stone, their flanks shrouded in darkness, their peaks sometimes climbing high enough to break the surface and give birth to new islands. Along the mid-ocean ridges, where tectonic plates gradually separate, long chains of volcanoes extend for tens of thousands of kilometers. These ridges crisscross the planet, like immense scars, stretching farther than any mountain range found on land. In these regions, magma rises from beneath the Earth's crust, forming new seafloor through a process that never truly pauses. Each year, a thin layer of newly formed basalt spreads outward, and the continents shift almost imperceptibly, carried along by the restless motion of the mantle below. If it were possible to observe this from above, the ocean floor would resemble a colossal zipper slowly opening, releasing both heat and life into the depths. Volcanic eruptions beneath the sea behave very differently from those on land. When molten rock encounters icy seawater, it cools almost instantly, solidifying into unusual rounded formations called pillow lavas. Columns of superheated water and dissolved minerals surge upward, mixing with colder water and creating plumes that can rise hundreds of meters before they fade away. At times, these eruptions are minor, remaining hidden and unnoticed. At other moments, they are immense, powerful enough to reshape entire landscapes in complete darkness. When such eruptions take place near coastlines or in shallow seas, they can transmit shock waves through the water, setting off tsunamis that travel across vast distances to reach distant shores. Because many of these volcanoes lie buried beneath kilometers of water, studying them directly is extraordinarily difficult. Extreme pressure can crush equipment, total darkness complicates navigation, and the intense heat surrounding eruptions can damage sensitive instruments. As a result, much of what we know comes indirectly. Seismic instruments detect faint tremors from afar, satellites notice subtle changes at the ocean's surface, and occasional expeditions unexpectedly encounter freshly formed lava fields. Each new finding highlights how much of Earth's geology remains hidden, unmapped, and constantly active. One of the most striking examples occurred in the Pacific in 2009, when scientists researching the Lau Basin captured images of an undersea eruption as it happened. Using a remotely operated vehicle, they observed fountains of lava bursting into the water, glowing orange even as the surrounding sea boiled into pale clouds. It was a rare glimpse of creation unfolding in real time, a vivid demonstration of how continents are built and how Earth continues to change. These underwater volcanoes are not only agents of destruction. Along their slopes, life has adapted in remarkable ways. Hydrothermal vents, often found near volcanic zones, release heat and chemicals that support distinctive ecosystems. Shrimp, crabs, and worms gather in enormous numbers, sustained by bacteria that convert chemical energy into nourishment. In an environment that seems utterly inhospitable, life thrives, showing that some of Earth's most dangerous landscapes can also be among its most productive. Still, the dangers cannot be ignored. When underwater volcanoes collapse or shift, they can trigger landslides that displace massive amounts of water. These sudden movements may generate tsunamis even more destructive than those caused by earthquakes alone. The Indian Ocean's tsunami of 2004, while primarily the result of a tectonic rupture, was influenced by submarine activity along the fault zone. It serves as a powerful reminder that events on the seafloor can send ripples outward, affecting lives far away on distant coasts. What makes submarine volcanoes so difficult to study is also what makes them so intriguing. They exist in places we can rarely access, across terrains we have scarcely mapped. Each one is a concealed mountain, a quiet builder of the planet, shaping oceans and shorelines without our awareness. And as we move deeper into the ocean, it becomes clear that the forces operating beneath the waves are not only molding Earth's surface but also recording the planet's story in fire and stone. For centuries, sailors told stories of enormous waves that rose suddenly from calm seas without warning. Walls of water taller than any ship, striking with such abrupt violence that entire vessels vanished. These tales were passed down as maritime legends, often dismissed by scientists on land as exaggerations born from exhaustion and fear. For a long time, rogue waves were treated as myths, placed alongside sea monsters and ghost ships. But in recent decades, the ocean has revealed that these unseen giants truly exist. In 1995, a wave slammed into an oil platform in the North Sea. Instruments measured its height at more than 85 feet, rising higher than the platform itself. The wave appeared suddenly, vastly larger than the surrounding seas, leaving no doubt that rogue waves are a real and formidable force. And it aligned closely with the descriptions sailors had been sharing for hundreds of years. For the first time, an event like this was captured with accurate measurements, and it compelled scientists to rethink stories that had long been brushed aside as exaggeration. From that point on, satellites monitoring the ocean surface began to confirm that rogue waves are not unusual flukes, but recurring phenomena that move across the seas unnoticed. A rogue wave can climb to more than 100 feet in height, higher than a 10-story building. Unlike tsunamis, which are caused by earthquakes or landslides, rogue waves appear suddenly in open ocean, often when several smaller waves align perfectly, combining their energy until one enormous wall of water rises above all the others. Their existence may be brief, but the destruction they cause can be immense. A ship caught directly in the path of one of these waves can be destroyed before there is even time to send a distress call. Some ships that were reported lost in calm conditions, with no obvious explanation, may have been taken by these sudden vertical walls of water. The enigma of rogue waves becomes even more striking when we consider how long they went unconfirmed. Despite centuries of eyewitness reports, solid proof was lacking until modern tools such as sea, surface radar, and satellite imaging made direct observation possible. When scientists began studying this data, they identified dozens of these waves forming across the world's oceans each year. Some emerged in the South Atlantic, others in the Pacific, and many appeared in areas like the North Sea, where strong storms meet powerful currents. In the end, it was not legend at all. It was a real phenomenon hiding in plain sight, moving too quickly, and vanishing too fast to leave clear evidence behind. Yet rogue waves are only one kind of giant concealed by the ocean. Even more devastating are mega tsunamis, events so extreme and uncommon that they are difficult to comprehend. Unlike ordinary tsunamis, which already possess extraordinary force, a mega tsunami can surge to heights exceeding 300 feet. These waves are not produced by tectonic movement beneath the seafloor, but by sudden and massive shifts of water. A landslide plunging into a narrow bay, a collapsing volcanic structure, or even the impact of an asteroid can displace enough water to create waves that rise above coastal mountains. One such event took place thousands of years ago in Alaska, when an enormous landslide fell into Lituya Bay. The resulting wave ripped trees from hillsides more than 500 feet above sea level, making it the highest wave ever recorded on Earth. The unsettling reality is that the forces capable of creating such events still exist today. The Canary Islands in the Atlantic, with their steep volcanic terrain, have been examined as possible sources of future megatsunamis. A collapse there could generate waves that travel across the ocean and strike the eastern seaboard of North America with catastrophic consequences. While the chances of this happening within our lifetimes may be low, the risk is not zero, serving as a reminder that the ocean contains powers greater than even the fiercest storms. What connects rogue waves and megatsunamis is the fact that they remain unseen until the instant they arrive. A seemingly calm sea can mask the buildup of immense energy, quietly accumulating beneath the surface until it suddenly focuses into a single, towering surge. For anyone who encounters such a moment, there is almost no warning, only the abrupt sight of water rising far beyond what the mind expects. These colossal forces, invisible until impact, remind us that the ocean is not only vast and mysterious, but also a place where scale itself can feel distorted. And just as the seas conceal these massive, destructive waves, they also hide regions where life slowly disappears, areas where the oxygen that sustains animals fades away, creating silent zones as lethal as any surge of water. Not every mystery of the ocean lies in its deepest trenches. Some of the most disturbing ones exist much closer to the surface, in places where living creatures quietly vanish. These areas are called oxygen dead zones, enormous sections of water where oxygen levels drop so low that larger animals cannot survive. Fish, crabs, and squid either escape or die, leaving behind waters that feel strangely lifeless. Only the smallest and toughest microbes remain, enduring conditions where oxygen is almost entirely absent. The ocean is normally full of motion, with currents mixing its layers, storms churning the surface, and waves constantly replenishing oxygen in the water. But in certain regions, this delicate balance breaks down. When rivers carry nutrient-rich runoff into the sea, it fuels massive blooms of algae. At first, the water can appear more vibrant than ever, thick with green plankton under the sun. But when the algae die, they sink to deeper layers where bacteria consume them. That breakdown process uses up oxygen, draining it from the surrounding water until almost nothing is left. Larger animals are unable to survive and slowly suffocate, and the sea takes on an eerie stillness. These regions can stretch across enormous distances. In the Gulf of Mexico, one dead zone often expands each summer to cover an area as large as some countries. Similar zones form off the coasts of India, South America, and Africa, where rivers deliver fertilizers and waste into the ocean. Climate change adds yet another layer of pressure. As surface waters grow warmer, they lose their ability to mix with the cooler, deeper layers below. Without this vertical mixing, oxygen cannot be carried downward, and the suffocating conditions spread into greater depths. With each passing year, these dead zones grow wider, transforming once lively ecosystems into silent, lifeless expanses. For those who attempt to explore them, these environments pose unique difficulties. Submersibles and remotely operated vehicles depend on oxygen sensors and finely tuned instruments, many of which struggle or fail in waters so depleted. The altered chemistry within dead zones can corrode metals, interfere with electronics, and reduce visibility. Equipment that performs reliably in open ocean conditions can quickly break down here, making it even harder to study places that seem to resist investigation. Entering these waters feels deeply unsettling. Where life would normally teem, there is instead an unnatural quiet, as if the ocean itself has been hushed. The organisms that manage to survive are remarkable examples of adaptation. Certain microbes endure without oxygen by using chemical reactions that draw energy from nitrogen, sulfur, or methane. Some release toxic byproducts, creating layers of water so hostile that almost nothing else can survive. These microbial communities may appear simple, yet they play a significant role in shaping ocean chemistry. They remind us that life is persistent, finding ways to continue even when conditions fall apart. Still, what exists here bears little resemblance to the richness found elsewhere, and the absence of fish or whales in these waters is profoundly noticeable. Dead zones are not always permanent. Storms, shifting currents, or changes in temperature can disturb the layers of water and reintroduce oxygen, allowing animals to return. But as climate change intensifies and human activity continues to load the seas with excess nutrients, these suffocating regions are forming more frequently and lasting longer. They signal a delicate balance being pushed too far, warnings that the ocean itself can begin to lose its breath. To picture the sea without its vast schools of fish, without the quick flashes of squid or the gentle drifting of jellyfish, is to imagine an ocean stripped of much of its wonder. Yet these places are real, quietly spreading beneath the surface. And as we move away from them into the broader ocean once again, we encounter other shadows waiting, not caused by a lack of oxygen, but by the presence of something that should never have reached these depths at all. Plastic has found its way into the deepest trenches on Earth. The deep ocean was long thought of as a realm beyond human influence, untouched by the noise and disorder of life on land. For centuries, it seemed impossible that anything we produced could travel so far, sinking into trenches and settling on the seabed miles beneath the surface. Yet when scientists began deploying robotic explorers into the planet's deepest chasms, the discoveries were disturbing. Even in the Mariana Trench, more than 10 kilometers below the waves, pieces of plastic were found. They were embedded in sediments, drifting in the water column, and even inside the bodies of animals brought up from the abyss. These fragments are known as microplastics, tiny particles less than 5 millimeters in size, often invisible to the naked eye. They form as larger plastic items such as bottles, bags, and fishing nets break apart under sunlight, waves, and time. Carried by ocean currents, they travel across the seas, sinking slowly until they scatter across the deepest valleys of the planet. They are light enough to remain afloat for years, yet so enduring that they may never fully break down. The same durability that once made plastic so valuable has turned it into a troubling presence throughout the ocean. What makes this discovery especially alarming is not only where the plastic ends up, but how it moves through living systems. Deep-sea amphipods collected from the Mariana Trench were found to have consumed microplastic fibers, their transparent bodies threaded with material that did not belong there. Mussels from coastal waters contain similar particles in their tissues. Fish brought up from mid-ocean depths reveal the same fragments in their stomachs. Even plankton, the base of the ocean's food web, have been observed ingesting these particles, mistaking them for nourishment. This shows that plastic is not merely settling on the ocean floor, but circulating through the very networks that support life in the sea. The magnitude of this issue is not easy to grasp. Researchers calculate that since the mid-20th century, humanity has produced billions of tons of plastic, and a significant portion of it has found its way into the ocean. Some of this material collects at the surface, drawn together by rotating currents into enormous gyres, creating floating accumulations that can span hundreds of kilometers. Far more, however, sinks quietly into the depths, hidden from view. In certain regions, cores extracted from the seafloor reveal sediment layers filled with plastic fibers, forming a new geological signal of our era. Should future civilizations ever examine these rocks, they will encounter the imprint of our time preserved in polymers. Even waters that appear distant and untouched are no longer free from this influence. Plastic particles have been identified in both the Arctic and the Antarctic, transported by winds and currents across entire hemispheres. They fall with rain, drift down with snow, and become embedded in the ice that seals the polar oceans. Each new finding intensifies a troubling question. How can we truly study the ocean in its natural state when we have already altered it so deeply? For scientists and explorers, this pollution presents both an obstacle and a contradiction. Instruments sent into the deep frequently return carrying samples that are already tainted, with microscopic plastic threads clinging invisibly to the water. Even within laboratories, extreme care is required to avoid adding more plastic to the very materials under investigation. The boundary between what is natural and what is artificial grows increasingly unclear, leaving us to imagine what the deep ocean once looked like before our influence reached it. And yet, despite the heavy implications of this knowledge, there is also persistence. Life in the depths continues, adjusting in ways we are only beginning to understand. Certain microbes have been identified that can break down specific kinds of plastic, using them as a source of energy. These organisms, surviving in the most unexpected environments, serve as a reminder of nature's remarkable ability to respond, even to pollution that seems beyond remedy. Still, the image remains: the darkest regions of Earth, once believed to be beyond human reach, now traced with strands of synthetic debris. As we move further into the story of the seas, a realization takes hold that we are not only uncovering the ocean's mysteries, but also confronting our own reflection within it, a reflection scattered in fragments of plastic that have become part of the deep itself. From this point, the ocean's story turns again toward the immense forces that shape the planet, the currents that influence climate and bind continents together, invisible pathways of water that move heat and life around the globe. Beneath the constantly shifting surface, hidden from everyday sight, a slow yet powerful circulation carries water throughout the world. It is commonly known as the ocean conveyor belt, a name that reflects both its steady motion and its critical role. Unlike the waves we watch breaking on shores, or the tides that rise and fall each day, this circulation operates over centuries, transporting heat, salt, and nutrients across immense distances. It links every ocean basin into a single global system, connecting the tropics with the poles and the surface with the deepest abyss. The process begins in the warm regions near the equator. There, sunlight warms the surface waters, and persistent winds drive them along consistent paths, forming major currents such as the Gulf Stream. This stream of warm water moves northward along the eastern coast of North America, carrying heat into the Atlantic Ocean. Along its journey, it releases warmth into the atmosphere, moderating winters in Europe and shaping weather patterns across vast areas. Without it, much of the northern hemisphere would experience far colder conditions. Farther north, in areas like the Labrador and Nordic seas, the situation shifts. Here, the warm surface waters cool, and as ice forms, salt is left behind, increasing the water's salinity. The water becomes so dense and heavy that it sinks into the depths. This sinking motion acts as one of the driving engines of the conveyor, drawing more warm water northward while forcing cold, dense water downward into the deep ocean. These deep currents then travel south, carrying cold and nutrients toward the Southern Ocean, where they circulate around Antarctica and divide into routes that eventually rise back toward the surface in distant regions of the Pacific and Indian Oceans. The conveyor belt is not defined by temperature alone. It is also essential for delivering oxygen to the deep ocean and nutrients to surface waters. When water sinks, it transports dissolved oxygen from the atmosphere into the depths. When it rises again, it brings with it the remains of countless organisms that have descended from the surface, supplying nutrients that support new life. Through this process, the conveyor weaves the ocean into a single, continuous cycle of renewal. Yet, this finely balanced system is vulnerable. Climate change poses a serious threat to the conditions that keep it functioning. As glaciers and ice sheets in Greenland and Antarctica melt, they release enormous volumes of fresh water into the ocean. Fresh water is lighter than salty water, and when excessive amounts enter northern seas, they reduce the salinity that allows water to become dense enough to sink. If the sinking process slows, the entire conveyor system can lose strength. Current research already indicates that the Atlantic segment of this circulation is decelerating, possibly reaching its weakest state in more than 1,000 years. The effects of such a disturbance would extend far beyond the oceans themselves, because weather patterns on land are deeply connected to the movement of seawater. A reduced Gulf Stream could bring colder, more severe winters to parts of Europe, intensify hurricanes in the Atlantic, and alter monsoon systems that billions of people rely on for water and food. Across South America and Africa, rainfall patterns could shift in ways that place agriculture at risk. Even the immense Amazon rainforest, often described as one of the planet's lungs, depends on moisture transported by this ocean conveyor. Gaining a clear understanding of these currents stands as one of the great challenges in modern science. Satellites are capable of tracking surface waters and measuring temperatures, yet the deep layers of the conveyor remain largely unseen. Instruments lowered into the depths, offer only brief glimpses, isolated measurements spread across decades. The scale involved is enormous, the forces are subtle, and the timescales are so vast that no single human life can ever witness the complete cycle. We chart distant stars with more precision than we trace these slow, hidden rivers of the deep. And yet their role is undeniable. They form the unseen framework of climate, the quiet connections that link weather, ecosystems, and life itself into a single, interdependent system. As we move further into this story, the currents that influence climate guide us toward other concealed domains, frozen frontiers where oceans lie trapped beneath ice, still waiting to be revealed. At the far edges of Earth exist regions where sea meets ice, frozen frontiers that can feel more otherworldly than familiar landscapes. The polar oceans, wrapped in cold and silence, extend beneath skies of faint light and long darkness. Their surfaces are bound by drifting ice sheets, but below, life persists in concealed waters that remain among the least explored places on Earth. These environments are both delicate and vast, where the boundary between ocean and land dissolves into frozen terrains that resist simple description. Antarctica lies at the center of this enigma. Beneath its massive ice sheets, some exceeding 4 kilometers in thickness, are hidden lakes sealed off from the atmosphere for millions of years. Among the most extraordinary is Lake Vostok. Larger than Lake Ontario, it rests under a towering cap of ice that has isolated it since long before humans appeared. Its waters have never been touched by wind or sunlight. Pressure from the ice above keeps the lake liquid, while geothermal warmth from deep within the planet adds a subtle heat. Within this concealed environment, scientists suspect that entirely unique ecosystems may exist, microbial life adapted to conditions unlike anything we know. Reaching it, however, presents immense challenges. Drilling through kilometers of ice carries the risk of contamination, and so Lake Vostok remains largely untouched. Known only through frozen water samples drawn up in ice cores, faint hints of a vast living system still undisturbed. The ocean encircling Antarctica tells a story of its own. Here, the Southern Ocean flows around the continent in a current so strong that it links all the world's oceans together. It is the only current that travels uninterrupted around the entire planet, unbroken by land, acting as a global pathway for nutrients and life. These waters are cold, dense, and rich in oxygen, sinking into the depths and fueling the conveyor belt that helps regulate Earth's climate. The life adapted to this environment reflects its extremes. Colossal squid roam the deep, penguins plunge into icy waves, tiny krill gather in numbers so immense that they rank among the most important species on Earth, sustaining whales, seals, and countless fish. Without the polar oceans, the balance and rhythm of the global seas would falter. The Arctic, though smaller in scale, is equally compelling. Here, sea ice expands and contracts with the seasons, spreading across millions of square kilometers in winter and retreating during summer months. This ice is more than frozen water. It forms a living habitat, supporting algae and plankton that cling to its underside and create the base of entire food webs. Polar bears hunt along its margins, seals surface through its cracks, and narwhals and belugas navigate its constantly changing maze. Beneath the ice, the Arctic Ocean conceals basins and ridges that remain only lightly mapped, regions so remote that very few scientific missions have ever reached them. The vulnerability of this area is striking. Rising temperatures cause ice to melt earlier each year, thinning a cover that has shaped the Arctic for thousands of years. As the ice withdraws, the delicate balance of life that depends on it is deeply disturbed. Exploring these frozen oceans ranks among the most difficult endeavors science has ever faced. Technology must withstand extreme cold, shifting ice, and isolation that can last for months. Submarines risk becoming trapped beneath ice sheets. Instruments freeze, power sources fail, and violent storms sever communication, reminding us just how challenging these final frontiers truly are. Even modern satellites find it difficult to peer through vast white stretches, as their signals are scattered by thick snow and persistent cloud cover. Because of this, much of what we understand about the polar oceans comes from incomplete pieces of information, assembled slowly, like brief views through heavy mist. What these fragments have revealed is remarkable. Yet, it is obvious that we have barely begun to explore what lies there. Antarctica's hidden lakes beneath the ice and the Arctic's constantly shifting ice fields continue to evade full observation, and in doing so, they point to something deeply important. These frozen regions are not lifeless deserts. They are active natural laboratories, places where Earth's secrets rest quietly. Encased beneath layers of ice are records of climate reaching back millions of years, stored in snow and ice that faithfully preserve every storm, every change in temperature, every trace of carbon dioxide. Within the cold waters themselves live organisms that may teach us how life endures in the most unforgiving conditions, and perhaps even offer clues to how life could exist on distant frozen moons. From this point, the narrative of the ocean extends once more, moving toward the tiniest inhabitants of the deep, microbes that survive where light and heat never arrive, guiding us into a hidden realm that transforms our understanding of what life is capable of. Far beneath the surface, in an environment that appears hostile to any living thing, there exists a concealed world. It is not dominated by whales or giant squid, nor by the fish and corals visible to our eyes. This domain belongs to the smallest residents of all, microscopic organisms that prosper in places once believed to be entirely unlivable. Their environment is not defined by forests or reefs, but by single cells that attach themselves to rock, drift with deep currents, or thrive within chemical plumes rising from the ocean floor. At hydrothermal vents, where dark clouds billow into the surrounding water, temperatures can rise beyond 300 degrees Celsius. Rather than perishing in such heat, microbes have adapted to make these vents their homes. They do not depend on sunlight, which cannot reach such depths, but instead draw energy from chemicals released from Earth's interior. Hydrogen sulfide, deadly to most life, becomes their source of fuel. Through these chemical processes, entire communities take shape. Tube worms, clams, and shrimp gather near the vents, living in close partnership with microbes that convert toxic substances into usable energy. What begins as invisible life forms becomes the base of ecosystems as complex and productive as tropical forests, all existing without any sunlight at all. In other regions of the ocean, methane seeps from the seafloor, slowly escaping from sediments below. For most organisms, methane offers no nourishment, yet certain microbes have evolved to use this gas as their energy source. By doing so, they create pockets of life where there would otherwise be nothing but empty mud. Mussels and other animals settle in these areas, relying on their microbial partners to survive. This ability to transform gas into food demonstrates a creativity in life that extends far beyond our everyday expectations. Some microbes go even further, feeding on substances that seem almost impossible to imagine as nourishment. Certain bacteria consume oil, breaking down slicks released into the sea. Others cling to metal surfaces, gradually extracting energy from iron and manganese. Some are even capable of digesting plastics, a development so recent and unexpected that scientists believe these organisms are evolving in response to human pollution. Everywhere in the ocean, no matter how extreme the conditions, there appears to be life ready to adapt and persist. The significance of these microbial worlds far exceeds their microscopic size. They do not simply survive in extreme environments. They actively shape the chemistry of the entire ocean. They recycle nutrients, filter harmful substances, and even influence the gases that move from the sea into the atmosphere. Without them, the planet's balance would be profoundly altered, yet we have examined only a tiny fraction of these organisms. Each journey into the deep brings back microbial samples never seen before. Many of them cannot be grown in laboratories and disappear once removed from their dark, high-pressure environments. Their mystery remains bound to the depths from which they come. What makes these microbes even more extraordinary is their potential value. Some produce compounds that could become antibiotics or treatments for cancer. Others create enzymes that may help break down plastic waste or unlock new forms of renewable energy. Within their tiny structures may lie solutions to some of humanity's most serious problems. There is, however, another side to this story. Microbes can also pose risks. Some thrive on toxins that could be dangerous if released, while others might alter environments in ways we do not yet fully understand. The deep ocean contains both opportunity and uncertainty, and within its microbial realms are secrets we are only beginning to glimpse. The story of these organisms reminds us that life's creativity surpasses our own imagination. As we scan the skies for signs of biology on other worlds, entire universes of microscopic life continue to flourish beneath our feet, waiting quietly in the darkness. From these concealed depths, the ocean draws us into even larger questions. Places where history itself is stored within layers of sand and sediment, preserving memories of Earth that reach back to the very beginning of time. The sea does not only shelter unknown creatures and unfamiliar landscapes, it also safeguards the forgotten stories of humanity. Beneath the waves rest traces of our own past, locked away in quiet darkness for centuries and, in many cases, for thousands of years. Across the seafloor lie countless shipwrecks, their wooden ribs and iron hulls slowly worn down by salt and the passing of time. Some of these vessels carried riches, others carried people, but every one of them carried a story. Each wreck represents a single frozen instant, a sudden halt in the forward motion of human ambition. In the Mediterranean, the water hides the galleys of ancient civilizations. Roman ships that once transported wine, olive oil, and marble along trade routes that connected distant lands. Amphorae remain scattered across the seabed, containers that once held the essentials of daily life. Their rounded forms are as familiar as pottery found on land, yet their resting place is the deep, where they have remained undisturbed since storms or warfare dragged them below. Farther north, off the coasts of Scandinavia, ships used by Viking raiders have been discovered, their wooden planks remarkably preserved by cold waters. These vessels, with carved prows and sails woven from wool, once cut through the seas with force and fearlessness. Now they lie still in darkness, silent reminders of an era when human bravery depended on delicate wooden structures. Every plank speaks of how far people were willing to travel, guided only by the stars above and the strength of their own oars. The sheer number of shipwrecks is astonishing. Historians estimate that there may be more than 3 million still resting on ocean floors around the world. They range from the powerful warships of the Spanish Armada to merchant vessels lost in the Indian Ocean. Together, they tell stories of expansion, commerce, hope, and tragedy. With each new expedition, divers and submersibles uncover fresh discoveries. Bronze cannons, porcelain dishes, coins marked with the names of forgotten empires, and even clothing preserved in extraordinary condition rise from their watery resting places. These finds are not merely objects, they are pieces of real lives once lived. Ships are not the only remnants hidden below the surface. Entire cities have also been claimed by the sea. Near the coast of Greece lies Pavlopetri, the oldest known submerged city, dating back more than 5,000 years. Its streets, courtyards, and building foundations can still be seen etched into the seafloor. People once walked there, traded goods, and raised families, until rising seas and shifting land pulled the settlement under, transforming a living community into a sealed time capsule. Other cities met similar ends. Heracleion, a major port of ancient Egypt, disappeared beneath the Mediterranean more than 1,000 years ago. Divers have since revealed massive statues of gods and pharaohs, fallen and resting in layers of silt. Great stone temples that once welcomed arriving ships now stand broken and tilted, their shapes softened by sand. Coins and jewelry lie scattered among the ruins, ordinary belongings abandoned during sudden disaster. These underwater remains blur the boundary between legend and fact. Cities once spoken of as myths are gradually emerging, not through stories passed down, but through the work of divers carrying lights and cameras into the depths. The preservation of these places is remarkable. Sunlight never reaches the deeper ruins, and oxygen barely penetrates them, slowing the process of decay. Fabrics, scrolls, and even food have been found intact inside sealed containers. Every dive becomes a direct encounter with a forgotten world, as though the ocean itself has been holding its breath for centuries, waiting for us to return. The ocean's lost history reminds us that the sea is more than a wilderness filled with unfamiliar life. It is also a vast archive of human memory. Every wreck, Every submerged street and every recovered artifact forms a page in a book far too large to ever fully read. Yet with each descent, another fragment is lifted back into the light, another story reclaimed from silence. And even as we study these reflections of ourselves, the ocean continues to guard deeper mysteries, secrets that lie far beyond the reach of recorded history, hidden within the dark labyrinths beneath the waves. From the surface, the ocean feels immense yet familiar. Waves roll in, tides rise and fall, and ships cross its expanse. But below, concealed in shadow, are places that give even experienced explorers pause. Among the most dangerous and least understood are underwater caves, enormous networks carved into stone by water over millions of years. These hidden corridors twist and turn, forming a black maze beneath coastlines, coral reefs, and continental shelves. Unlike the open sea, where escape is at least possible, a cave offers no mercy. Once inside, there is only one exit, and reaching it can be more perilous than the descent itself. Divers who have entered these submerged chambers describe them as unlike anything else on Earth. As soon as a narrow beam of light sweeps across the rock walls, the hidden space begins to reveal shapes carved patiently over immense spans of time. Stalactites still hang from ceilings where they once formed in open air, clear evidence that many of these caves were dry thousands of years ago, during ice ages when sea levels were far lower than today. When the oceans rose, the caves flooded, locking away an untouched archive of ancient climates and long-lost landscapes. In certain locations, the remains of extinct animals have been found, preserved within the cold, oxygen-poor water. These caves are far more than simple geological structures. They act as time capsules, preserving clues about what Earth was like in the distant past. Yet their beauty is inseparable from danger. Submerged caves are often described as more hazardous than spacewalks. An astronaut in space is secured by a tether, supported by constant communication, and surrounded by the open view of the stars. A diver inside a cave has only a single guideline to follow back out, while the walls press in with an overwhelming, suffocating silence. The risks are extreme. A malfunctioning piece of equipment or a single wrong decision can mean death. There is no surface to break through for air, only solid rock and endless water in every direction. Many divers have lost their lives in these environments, and their experiences are passed through the diving community as stark reminders of how unforgiving this dark maze can be. Mapping these places is extraordinarily difficult. Unlike the open ocean, which can be surveyed using sonar or satellites, caves have no simple shape. Some tunnels narrow so tightly that only one diver can slip through at a time. Others expand suddenly into enormous chambers that feel like underwater cathedrals, their ceilings vanishing into total darkness. Deeper still, some passages stop abruptly at solid walls, while others plunge straight down into vertical shafts with no visible end. Because of this complexity, no two cave systems are alike, and many have never been fully charted. Explorers depend on reels of guideline to find their way back, a delicate lifeline within a vast, winding labyrinth. In places such as the Yucatan Peninsula, underwater cave systems known as cenotes extend for hundreds of kilometers beneath the limestone bedrock. Divers there have uncovered human remains from ancient cultures, along with offerings placed during sacred ceremonies. These finds remind us that caves are not only natural marvels, but also deeply connected to human history and belief. Elsewhere, including regions like the Bahamas, massive blue holes drop straight down into the earth, hiding layers of toxic water where most life struggles to exist. Every cave system tells its own story, and each one presents a unique scientific challenge. Our understanding of these environments is still at a very early stage. Unusual creatures such as blind fish, pale shrimp, and nearly transparent eels inhabit these spaces, specially adapted to life without sunlight. Some of these species exist nowhere else on the planet. In this permanent darkness, evolution has taken unusual paths, producing life forms that demonstrate just how adaptable and inventive biology can be under extreme conditions. Exploring submerged caves is like stepping into the planet's hidden lungs, silent and breathing secrets that reach back into prehistory. They allow us only brief glimpses before reminding us of their dangers. Even with modern tools, rebreathers, and powerful lights, these caves remain deeply mysterious. They are the sea's black labyrinths, harsh, beautiful, and nearly impossible to fully know, each passage reinforcing how little of this world we have truly explored beneath the moving waves. In regions where sunlight never reaches, there exist animals that seem as though they belong to myth or imagination, yet they are entirely real, shaped by evolution in ways so strange they challenge belief. In the twilight and abyssal depths of the ocean, life has followed routes utterly unlike those of shallow waters or land. These organisms show us that the rules of survival can be stretched into forms that feel both alien and unexpectedly elegant. One of the most unsettling examples is the goblin shark, often described as a living fossil because its ancestry extends back tens of millions of years. With its elongated, flattened snout and a jaw that can suddenly thrust forward like a spring-loaded trap, it stands apart from every other shark on Earth. Its thin, nail-like teeth are perfectly suited for gripping slippery prey in darkness. In images, its pinkish skin and pale, ghostly eyes give it an unreal appearance, as if it belongs more to a nightmare than the ocean. Yet, it is a calm hunter, drifting through the shadows at depths far beyond human sight, perfectly designed for a world where surprise and stealth determine survival. Deeper still moves the vampire squid, a creature whose name suggests horror, though in reality it is a gentle scavenger, feeding not on blood, but on marine snow, the steady fall of organic material drifting down from the sunlit surface above. Its body is wrapped in a cloak-like webbing that stretches between its arms, and when it feels threatened, it can invert itself, revealing spiny filaments that appear far more intimidating than they truly are. Its skin emits a soft bioluminescent glow, tiny points of light that shimmer like distant stars suspended in the abyss. Rather than being a monster of the deep, the vampire squid is a masterpiece of efficiency, perfectly adapted to survive in regions where oxygen levels are so low that most other animals would suffocate. Then there is the anglerfish, one of the most recognizable predators of the deep ocean. The female carries a living lantern, a glowing lure that hangs from her head and tempts prey toward her enormous mouth. Her teeth curve inward like barbs, making escape impossible once a victim is caught. In the crushing darkness of the abyss, she remains perfectly still, a solitary light in the void, waiting patiently until an unwary fish drifts too close. Even more astonishing is her method of reproduction. The males are incredibly small compared to the females, so tiny that they seem almost like a separate species. When a male finally encounters a female, he attaches himself to her body, gradually fusing with her as his organs wither away until he becomes little more than a permanent source of sperm. This extraordinary arrangement ensures that, even in the vast emptiness of the deep where encounters are rare, reproduction can still occur. These creatures are only a small sample of the ocean's most surreal residents, and even they barely hint at what is possible. In the depths, where pressures would easily crush human-built submarines, evolution has produced countless other remarkable solutions. Some fish possess transparent heads, allowing their eyes to look upward through clear tissue as they scan for the faint outlines of prey above. Others have mouths that open wider than their entire bodies, enabling them to swallow animals larger than themselves in a single motion. There are organisms with bodies so gelatinous that they lose their shape when brought to the surface. Some beings cannot even be properly studied outside their native environment because the fragile balance of pressure and temperature that sustains them cannot be recreated in a laboratory. Every remotely operated vehicle sent into the deep seems to encounter life that has never been documented before. Sometimes it is an unfamiliar species of jellyfish, drifting through the darkness with colors that glow like stained glass. Sometimes it is a worm that shines in shifting patterns of blue and green. Each new discovery serves as a reminder that the ocean, vast and secretive, contains forms of life we have barely begun to imagine. For every goblin shark or anglerfish we recognize, there may be dozens more hidden within trenches, ridges, and unexplored canyons. Perhaps the most surprising realization is that these animals, as alien as they appear, are not monsters. They are not mistakes. They are solutions. Each one is an answer to the same essential question. How do you survive in a place without light, where food is scarce, and where the environment seems intent on crushing you at every moment? The adaptations they display are not mere curiosities. They are blueprints for resilience, proof that life is not bound by narrow rules. It bends, it adapts, and it invents entirely new ways to exist. As scientists continue to explore these black waters, every image and every sample pushes the limits of what we believed was possible. The creatures of the abyss are not only wonders of biology, they are clues to what life elsewhere in the universe might look like. If such strangeness can flourish here, on our own planet, then the idea of life in other hidden oceans, beneath the icy shells of distant moons, feels increasingly plausible. Far below the restless surface, where the seafloor stretches for thousands of miles, lie mysteries that science has yet to unravel. The ocean is vast enough to engulf continents and deep enough to conceal worlds within worlds, and within that immensity it guards secrets that evade even our most advanced tools. Sonar sends pulses through the water that bounce back from the seafloor, revealing the unseen, yet sometimes those echoes return with shapes and signals that defy understanding. Strange contacts appear on screens, too large to be dismissed as whales, too irregular to resemble geological formations. Yet, when ships or remotely operated vehicles are dispatched to investigate, the signals fade away, as if whatever produced them simply dissolved into the water. For decades, scientists and naval crews have reported these anomalies, catalogued them, and debated their meaning. Some may be distortions caused by layers of varying temperature in the ocean. Others could be migrations of poorly understood species. But many remain unanswered, their true origins lost in the deep silence. The ocean has always been a place where things vanish. Ships made of steel and guided by satellites still disappear without a trace, their last known positions consumed by storms or currents. Some may be destroyed by rogue waves, towering walls of water that rise suddenly and leave no survivors to explain what happened. Others may be dragged down by hidden reefs or seafloor ridges that are only partially mapped. And then there are the cases where no explanation is ever found, where vessels vanish on calm seas without sending a single distress call. The ocean leaves behind very little trace, dispersing wreckage over vast distances or sealing it beneath layers of sediment in a matter of hours. Even in an era of worldwide monitoring and constant surveillance, unanswered questions endure, reminding us that this immense water world has not been fully mastered by technology. Beneath the surface lie not only vanished vessels, but entire landscapes that stretch our understanding of Earth itself. Across the seafloor, spanning thousands of miles, stand formations that resemble enormous geometric ridges, spirals, and concentric shapes carved into solid rock. Some of these structures may be the result of ancient volcanic activity frozen into forms that look unfamiliar to us today. Others could be created by minerals slowly accumulating in patterns rarely seen on land. And at times, as with the Baltic Sea anomaly or other puzzling sonar readings, the shapes appear almost too orderly, too exact, as if they were shaped by intention rather than by chance. Oceanographers remain careful in their interpretations, fully aware of how easily sonar imagery can be misleading and how frequently the ocean sculpts rock into unexpected forms. Still, every new anomaly reinforces the sense that the seafloor contains geological features whose origins remain beyond our present explanations. There are also the strange sounds that move through the ocean, captured by hydrophones yet never clearly identified. Deep rumbles that persist for minutes, pulses that travel across entire basins, and clicks or calls that do not correspond to any known creature. Some of these signals may connect to unusual sonar features. Others could be tied to shifting tectonic plates or underwater volcanic activity. Yet in many instances, no definitive explanation has ever been reached. Scientists log them with names such as the Blue Port Julia, quiet reminders of how much of the ocean's acoustic world remains unexplored. Even in locations where humans have ventured deepest, such as the Mariana Trench, each discovery seems to raise more questions than answers. Unexpected ridges emerge from the depths, Sediments move like slow rivers along the ocean floor, and luminous organisms appear briefly in the glow of cameras before fading back into darkness. For every answer gained through exploration, many more mysteries arise, widening the gap between what we understand and what we merely suspect. The ocean is not only the birthplace of life, but also a vast, restless archive of unanswered questions. Sonar contacts that disappear without warning, ships that sink silently into obscurity, geological structures that seem almost alien, and sounds with no clear source, all serve as reminders that our planet still contains regions where mystery prevails. The next stage of discovery lies not only in solving these riddles, but also in recognizing that the ocean will always guard some of its secrets beyond our reach, even as we continue to push deeper. Despite the achievements of modern science, despite the rockets launched into orbit and the probes sent toward the far edges of the solar system, our capacity to explore the ocean remains surprisingly limited. The tools we possess, impressive as they are, struggle against the sheer scale and hostility of the deep. Even the most advanced machines falter when confronted with crushing pressure, immense distances, and the unforgiving nature of the sea. Human-occupied submersibles stand among the most recognizable instruments we have for reaching the depths. They are remarkable feats of engineering. Capsule-shaped and encased in steel or titanium walls, thicker than the vaults protecting our most valuable treasures. Yet this strength comes at a high price. Every descent demands enormous preparation, highly trained crews, and specialized ships to transport them offshore. A single dive may last only a few hours, even after months or years of planning. These submersibles can descend only a limited number of times before extensive maintenance is required, and only a small number exist worldwide that are capable of reaching the deepest trenches. As a result, human exploration of the ocean is rare, reserved for a handful of dedicated scientists or occasional adventurers willing to accept great risk for a brief glimpse into the abyss. To push beyond these limits, remotely operated vehicles, known as ROVs, are often deployed where humans cannot safely go. They drift through the darkness, connected to surface ships by long, heavy cables that supply power and communication. Their cameras reveal haunting images of landscapes never seen before, while robotic arms collect samples from vents and trenches. Yet they too are vulnerable, constantly challenged by the very conditions they are designed to endure. Cables can snap under strain, equipment can be crushed or clogged by drifting sediments, and immense pressure can deform even carefully engineered housings. Each ROV is expensive to construct and operate, and many have been lost to the depths, disappearing into regions where recovery is impossible. Their operational lifespans are brief, and their missions pass quickly, which leaves the ocean largely unexplored and mostly untouched. Satellites, which have completely transformed how we study outer space, encounter a hard boundary when they face the ocean. From orbit, their instruments can outline continents, follow the movement of currents, and even detect tiny changes in sea surface height that suggest mountains and trenches far below. But they cannot see directly into the depths. Light and radio waves scatter and fade after traveling only a few meters through water, rendering the vast interior of the ocean invisible to their view. At best, satellites offer vague shadows and softened hints of what lies beneath, never the sharp, detailed images they provide of distant planets and stars. This limitation makes the difference between ocean exploration and space exploration even more striking. Telescopes can look across billions of light-years, producing clear portraits of galaxies that formed long before Earth existed. Yet sonar, our main tool for studying the seafloor, struggles to penetrate more than a few kilometers with any real clarity. The deeper we attempt to observe, the less distinct the picture becomes. Creating a detailed map of the entire ocean would require centuries using current technology, and even then, the constantly changing nature of the sea means no map could ever stay truly complete. The sheer scale of the ocean acts as its strongest shield against our efforts to understand it. Every technology we rely on, from submarines and ROVs to satellites, has limits that make the dream of fully exploring the sea feel nearly unreachable. For now, what we possess is only a collection of fragments, rare descents into deep trenches, brief glimpses captured by delicate robots, and faint outlines detected by satellites high above. Each fragment adds something to our understanding, yet the overall picture is destined to remain unfinished. And so the ocean keeps its secrets, not only because it is immense and hostile, but because our machines, remarkable as they are, still cannot match the scale of its vastness. The sea reminds us that even as we reach outward toward the stars, we are still humbled by the depths of our own planet. The ocean is not merely deep and mysterious, it is vast beyond easy comprehension. When scientists describe its scale, the figures involved are almost impossible to picture. The total volume of Earth's oceans is estimated to exceed 350 quintillion gallons of water, a number so enormous it stretches far beyond what the human mind can easily grasp. To put that into perspective, if every person alive today attempted to count each gallon one by one, working non-stop without rest, the task would take longer than all of recorded history. The sea is not just wide, it is immeasurable in its immensity. A body of water so expansive that our attempts to fully explore it begin to seem almost absurd when measured against its true size. Exploration depends on tools, but those tools must operate within strict limits of time and energy. Sonar pulses can scan the seafloor, returning echoes that sketch the outlines of ridges and trenches. Yet each scan covers only a very small area. Ships dragging sonar equipment move slowly across the surface, sending beams downward to piece together an image of what lies below. If we tried to survey every part of the ocean this way, working continuously without stopping, the effort would not be completed for thousands upon thousands of years. And by the time the final section was mapped, the earliest maps would already be outdated, as currents shift sediments, volcanoes reshape ridges, and new fractures open in the planet's restless crust. Even satellites, which provide broad views of the ocean's form, cannot escape the problem of scale. They detect slight variations in sea surface height, revealing the gravitational pull of seamounts and trenches far below, but the details remain soft and indistinct, like shadows seen through thick fog. Turning those shadows into clear images requires close, careful work, and that kind of work takes time. A single research expedition may return with astonishing discoveries, but when compared to the entire ocean, it is like studying one drop of rain to understand a whole storm. This immense scale affects not only mapping, but discovery itself. Each remotely operated vehicle that descends into the dark explores only a tiny cone of space, a narrow slice of the abyss. Even if thousands of such dives were carried out, they would barely scratch the surface of the deep. Every time a new creature is recorded or an unfamiliar landscape comes into view, it is accompanied by the awareness that countless more remain hidden, waiting in the endless expanse that has never been reached by light or lens. The ocean is never still. Its waters move endlessly, circulating through vast patterns that unfold over centuries. Currents bend, spiral, and intertwine, transporting heat, nutrients, and living organisms across entire ocean basins. A single gallon of seawater taken from the surface might not arrive back at that same location for hundreds of years, carried along by this immense global conveyor of circulation. Over such spans of time, environments transform, species evolve or disappear entirely, and the shape of the sea floor itself can change. Because of this, exploration is not just a question of how far we can go, but of time itself, as the subject we try to study continues to shift before it can ever be fully understood. To describe this challenge as mathematically impossible is not an overstatement. Imagine countless scanning vessels spread across the seas, each one emitting sonar signals day and night. Imagine swarms of robotic submersibles moving through every layer of depth. Even under those conditions, the sheer volume of the ocean would overwhelm them. It serves as a reminder that the sea is not a controlled laboratory that can be neatly organized and recorded, but a living, dynamic system so vast that its mysteries will always move faster than our ability to grasp them. And perhaps this is part of the ocean's lasting strength. Its immense scale ensures it can never be completely known. It preserves mystery in a world where so much else has already been mapped, measured, and catalogued. No matter how advanced our technology becomes, the numbers do not change, and the ocean continues to show us that some frontiers are simply too large to be mastered. When we look at how humanity allocates its resources, the contrast is impossible to ignore. Every year, billions upon billions of dollars are devoted to exploring space. Rockets rise skyward carrying cameras and scientific instruments. Satellites are launched in large numbers, and bold plans are drawn up for Mars and worlds even farther away. Meanwhile, the oceans, which cover more than 70% of Earth's surface and contain an enormous share of its unknowns, receive only a fraction of that attention. By comparison, funding is scarce, research ships are limited, and scientists who dedicate their lives to studying the sea often struggle just to secure enough money for a single expedition. This gap does not reflect a lack of importance. The oceans shape Earth's climate, sustain billions of people through food, and hold vast potential for new medicines, minerals, and energy resources. Yet, in political and public imagination, the seafloor lacks the spectacle of the sky above. Space has always been wrapped in drama, in the idea of new worlds, distant civilizations, and the symbolic triumph of reaching beyond our planet. The ocean, just as alien and just as mysterious, remains concealed in darkness and quiet, far from the view of those who make decisions. It does not captivate audiences in the same way a rocket launch does, and as a result, the drive to explore it is far weaker. As a consequence, ocean science is often confined to brief and fragile opportunities. Research teams may wait years for access to a vessel, and when that chance finally arrives, every hour at sea becomes precious. Expeditions must be planned with extreme care because funding rarely allows for repeat missions. The tools they rely on are costly to maintain, and if a critical instrument fails under the immense pressure of the deep, it may be lost forever. Even building specialized submarines or remotely operated vehicles frequently depends on private donors or partnerships with industries like oil and gas, which come with their own priorities and goals. This reliance often means that pure scientific exploration is pushed aside in favor of projects with clear economic value. The imbalance becomes even clearer when we consider scale. Space agencies operate massive facilities, employ vast teams of engineers, and receive consistent funding that supports ongoing development. In contrast, oceanography in many regions relies on aging ships, instruments repaired again and again with limited resources, and scientists who spend nearly as much time writing grant proposals as they do conducting research. The promise is extraordinary, yet the tools needed to unlock it remain frustratingly out of reach. What makes this even more striking is that discoveries from the deep ocean could affect our daily lives almost immediately. Microorganisms living near underwater vents may offer paths to new antibiotics. A deeper understanding of fish populations could help manage them sustainably, protecting food supplies for future generations. Detailed knowledge of ocean currents could improve climate models and lead to more accurate forecasts of storms and droughts. But without sufficient investment, progress comes slowly and unevenly, leaving critical insights incomplete and leaving us less prepared for changes already underway. Some scientists speak of a blue space race, a future where exploring the oceans is treated with the same urgency as exploring space, but for now, that vision remains distant. Governments remain cautious, private investors look for faster returns, and much of the public remains unaware of just how much of our own planet is still hidden beneath the waves. The ocean goes on waiting, quietly and patiently, just as it has for millions of years, while our collective focus keeps drifting elsewhere. And so the familiar pattern repeats itself. Rockets rise dramatically into the sky, while research vessels move almost unnoticed across the waves. Telescopes peer deep into faraway galaxies, while sonar systems struggle to chart trenches only a few miles from land. This imbalance is not about what matters more, but about where human imagination chooses to roam. That lack of sustained attention means vast areas of the ocean will stay unmapped, not because they cannot be reached, but because our determination to explore them has never truly matched their real worth. Each time humanity tries to venture into the deep, it steps into an environment that pushes back at every moment. The ocean is not a passive space. It responds with forces that challenge both human bodies and the machines we build. It is a domain where every change in temperature, every added ton of pressure, and every extra mile of distance increases the danger. Exploration here is not driven by curiosity alone. It is a calculated risk, and every descent carries the full weight of that risk with it. Cold is one of the earliest and most persistent threats encountered. The deeper the descent, the farther one moves away from the warmth of the sunlit surface above. Temperatures drop steadily until they settle just above freezing. A cold so intense it penetrates steel and titanium, pushing insulation to its limits. For human divers, even inside protective suits, this cold can cause numbness, exhaustion, and loss of coordination. For machines, it slows battery chemistry, thickens lubricants, and makes materials more fragile. The deep sea does not need to strike aggressively. Its cold alone is enough to weaken and destroy what enters its realm. Pressure, however, is the harsher opponent. With every 10 meters of depth, the mass of water overhead grows heavier. By the time a vessel descends to 1,000 meters, the force squeezing its structure is already 100 times greater than the pressure at the surface. In the deepest trenches, that force increases to more than 1,000 times what we experience above. To survive, submersibles must be constructed like armored strongholds, with walls thicker than vaults and curved shapes designed to spread stress evenly. Even so, the room for error is almost non-existent. A flaw no wider than a strand of hair can trigger a sudden and total collapse. Machines, no matter how advanced, live under this constant threat, and for the humans sealed inside them, the awareness of that danger never fades. Isolation adds another layer of risk. Once an expedition leaves the surface, it enters a world where communication becomes slow and limited. Radio waves cannot travel through seawater, so the instant connections that guide astronauts or aircraft pilots simply do not exist. Information must move as sound through the ocean, delayed and distorted, or through long cables linking fragile vehicles to ships far above. When something fails, assistance cannot arrive quickly. A trapped diver or a disabled submersible is isolated, far beyond the easy reach of rescue. This separation is a central reason why each journey into the depths feels so grave. Those who descend understand that the ocean rarely offers second chances. For human divers, biological limits intensify these dangers. Human lungs are not designed to withstand extreme pressure, and body tissues react unpredictably to compressed gases. Too much nitrogen can impair the brain, causing confusion and poor decisions. Oxygen, at high pressures, can become poisonous. Even the return to the surface is perilous, as expanding gases can form bubbles in the body, leading to serious injury or death. Specialized training and equipment push the boundaries of what humans can endure, but those boundaries remain tight, leaving most of the deep ocean completely inaccessible to the human body. Machines are meant to extend our reach beyond those limits, yet they too fail. Cables snag and snap, propellers clog with sediment, cameras crack under crushing pressure, and electronics slowly corrode in salt water. At times, entire vehicles are lost, slipping quietly into the abyss with no hope of recovery. Every expedition carries the risk of loss, whether that loss is costly equipment, irreplaceable data, or, in rare and heartbreaking cases, human life. Still, explorers are drawn back to the ocean time and time again, compelled by the lure of what remains hidden from view. The dangers never fully disappear, yet every dive that succeeds offers a fleeting glimpse into what exists within the darkness. Extreme cold, crushing pressure, and profound isolation turn the deep sea into a harsh and unforgiving frontier. But those same conditions also make it deeply humbling, a reminder that true discovery often happens right at the limits of human endurance. The ocean is not only something that spreads across the face of our planet. In many ways, it serves as a memory, an archive preserved not in written language or digital storage, but in the slow and silent accumulation of sediments drifting downward through the water. Every grain of sand, every speck of dust, every shell from a microscopic organism that falls from above eventually comes to rest on the ocean floor. Over long stretches of time, these materials are pressed together into delicate layers, each one settling atop the last, forming pages in an immense geological journal. Within these layers rests the story of Earth itself, a chronicle of changing climates, mass extinctions, species that rose and disappeared, and the powerful forces that have shaped the planet over millions of years. When scientists extract core samples from the deep ocean, they are effectively retrieving time capsules. A single narrow cylinder of mud can contain hundreds of thousands of years of history, with each centimeter marking centuries of transformation. Inside those subtle bands of sediment, locked away in chemical signals and microscopic fossils, are hints about past temperatures, patterns of rainfall, and even the makeup of the atmosphere at the moment those layers formed. In certain strata, researchers uncover clear signs of catastrophe, such as the sharp increase in iridium that signals the asteroid impact responsible for ending the age of the dinosaurs. In others, they observe the slow rhythms of ice ages, preserved in the shells of plankton whose chemistry reflects the oceans they once inhabited. Yet gaining access to this memory is anything but simple. The deep seafloor is not like a shelf of books waiting to be opened. It is an environment that is fragile, sensitive, and easily damaged. Simply lowering instruments can stir up sediments, wiping away the fine details scientists seek to protect. Vehicles that touch down on the seabed may crush habitats of organisms that have existed undisturbed for centuries. Even careful drilling carries the risk of blending layers together, smearing the sequence of events that nature recorded so patiently across vast spans of time. The challenge lies not only in reaching the ocean floor, but in doing so while keeping its history intact. Adding to this difficulty is the sheer scale of the ocean's archives. Sediments are far from uniform. They vary with depth, with distance from land, and with the shifting patterns of ocean currents. One core sample may tell the story of a volcanic eruption that filled the skies with ash thousands of years ago, while another, collected just a few hundred miles away, might reveal the slow buildup of nutrients that once fueled bursts of life. Creating a global picture from these clues demands countless samples, gathered from scattered locations across a seafloor that spans more than 200 million square miles. It is a puzzle of such magnitude that even the most committed research teams can only ever assemble pieces of it. Yet within those pieces lie remarkable revelations. Deep layers of sediment have exposed cycles of warming and cooling that occurred long before humans existed, showing how finely balanced Earth's climate has always been. Other layers have preserved evidence of ancient tsunamis, their immense power frozen in sudden deposits of sand carried far from shore. In some regions, sediments contain the remains of organisms so tiny they are visible only under a microscope, but within their shells and chemical fingerprints is information about oceans that existed tens of millions of years ago. These records reach further back than any human-made document, further than the oldest cave paintings or clay tablets, offering windows into worlds no human ever witnessed. And while these natural archives are invaluable to science, they are also increasingly at risk. Human activities, from deep-sea trawling to mineral extraction, threaten to disrupt sediments on an unprecedented scale. What took millions of years to record can be destroyed in moments by heavy machinery dragged across the ocean floor. This danger hangs over modern exploration, raising difficult questions about how much of the ocean's memory might vanish before we have had the chance to read it. Even so, the ocean continues to add to its record every single day. Dust carried on, the wind settles into its depths. Ash from distant volcanic eruptions drifts down through the water. Shells sink slowly, and the remains of living creatures descend to become part of the archive. Layer upon layer accumulates, building a living memory that grows deeper with each passing century. It waits in silence, calm and immense, patiently holding the story of Earth in forms we are only beginning to grasp. As humanity moves forward into new eras of discovery, the ocean remains a quiet witness. Ever since humans first stood on shorelines and looked out over the water, there has been a deep desire to understand what exists below the surface. The sea has always lived in our imagination, a place that inspired both awe and fear. Yet for most of human history it remained an inaccessible boundary. Reaching its deepest regions once felt as unrealistic as reaching the stars themselves. That began to change in the 20th century, when daring efforts were made to cross that boundary, to send people down into the abyss and uncover what it concealed. One of the earliest and most famous attempts took place in 1960, when a vessel known as the Trieste descended into the Mariana Trench. This trench, concealed beneath the western Pacific Ocean, is the deepest known location on Earth, and the Trieste carried 2 men all the way to its floor. The vessel did not resemble a sleek submarine. Instead, it was built like a bathyscaphe, with a rounded pressure chamber engineered to survive the immense forces of the deep. Its walls were incredibly thick and heavy, so much so that the craft could descend only at a slow pace, sinking for hours through the water column before finally reaching the bottom. When it eventually settled on the seafloor, almost 11 kilometers beneath the ocean's surface, the men inside looked through a small viewing port and witnessed a landscape no human had ever seen before. Their stay was brief before they began the long ascent back towards sunlight, but that descent marked a historic moment. Humanity had reached the deepest frontier of the planet, if only for a short time, yet that achievement did not spark an era of regular exploration. In the decades that followed, almost no one returned to those depths. The explanation was straightforward. The expense and complexity were staggering. Designing a vehicle capable of surviving such crushing pressure was an enormous engineering challenge. Supporting a mission required specialized ships, skilled crews, and flawless coordination, while the danger of failure was ever present. The deep ocean offered no easy rewards, and the Trieste's journey remained unequaled for more than 50 years. It was not until the early 21st century that another human would descend again, this time alone. In 2012, filmmaker and explorer James Cameron piloted a custom-built submersible into the Challenger Deep, the same section of the trench first reached in 1960. His vehicle, named the Deep-Sea Challenger, was tall and narrow, filled with powerful lights and advanced cameras. Unlike the Trieste, which had very limited ability to record its surroundings, Cameron's craft was designed to document what it encountered and collect samples. He spent several hours exploring the seafloor before returning to the surface, offering the first modern view of the deepest part of the global ocean. The event captured worldwide attention, not only because of the achievement itself, but because it underscored the fact that more than half a century had passed since the last visit. Between those landmark dives and in the years since, only a small number of missions have reached full ocean depth. Each journey has revealed more about the life that survives in those dark trenches, but each has also made clear how limited our access remains. The pressure at such depths is so extreme that every dive carries the risk of total failure. Even the most carefully designed machines must undergo repeated testing before being trusted. Their structures are pushed close to their limits long before they ever carry a human. A single mission can cost millions of dollars, and while the scientific returns are valuable, they represent only a tiny glimpse of what is still concealed. The truth is that despite centuries of ocean travel, and despite living in an age of satellites and space exploration, fewer people have stood on the ocean floor than have walked on the moon. Those few individuals who have descended so far symbolize human perseverance, but they also reveal the boundaries imposed by technology and resources. Each mission showcases remarkable ingenuity, while at the same time emphasizing the sheer scale of the challenge. What has been accomplished is extraordinary, yet when compared with the vastness of the oceans, it serves as a reminder that we have barely scratched the surface of a realm that may never be fully understood. When discussions turn to the future of ocean exploration, they are often filled with both optimism and caution. On one hand, there is confidence in emerging technologies that may allow deeper and longer missions than ever before. On the other, there is the sobering reality that the difficulties of the deep have always outweighed human ambition. The ocean has waited patiently for millions of years, and it remains uncertain whether the next generation of machines will truly unlock its secrets or simply pass lightly over the surface of its enduring mystery. Among the most widely discussed possibilities are autonomous submersibles guided by artificial intelligence. Unlike crewed vehicles, these machines could operate for weeks or even months without rest, descending into trenches and moving across the seafloor in regions far too dangerous for humans to enter. They would not grow tired, they would not feel fear, and they would not need constant human oversight. Large groups of them could be released much like schools of mechanical fish, each unit equipped with cameras and sensors, exchanging data with the others, and building detailed maps of regions no single research vessel could ever hope to cover. In principle, this approach could make the overwhelming scale of the ocean easier to handle, dividing something immense into portions small enough to examine carefully. Yet even the most sophisticated machines remain constrained by the harsh conditions they are sent into. Batteries lose power rapidly in extreme cold, and sensitive electronics slowly degrade in corrosive salt water. With every additional mile of depth, pressure increases to levels that strain every seal, joint, and structural connection. One minor design weakness can lead to the silent failure of a machine, disappearing forever into the darkness below. Although artificial intelligence can help machines navigate and adapt, it still cannot fully overcome the brutal physical forces of the deep. For now, these visions of vast robotic swarms exist largely in research facilities and experimental models rather than in everyday reality. Discussions about what comes next often return to a familiar issue: money. Pure scientific curiosity has rarely been enough on its own to support large-scale exploration of the deep ocean. Instead, many emerging technologies are closely linked to industries that view the ocean primarily as a source of materials. Deep-sea mining, for instance, is promoted as a method for collecting valuable minerals from the seabed. Elements used in electronics, batteries, and renewable energy technologies. Corporations are pouring resources into machines capable of traveling to abyssal plains, gathering nodules rich in rare metals, and transporting them to the surface for processing. Some suggest that these activities could unintentionally improve our understanding of the deep, since mining operations require detailed surveys of extensive seafloor regions. But this is where a conflict emerges. Exploration motivated by profit is fundamentally different from exploration inspired by curiosity. Mining equipment is built to remove and consume, not to observe and preserve. And the fragile environments of the deep may be disrupted before they are even properly studied. What little we currently understand about hydrothermal vents and abyssal ecosystems indicates that they support species found nowhere else on Earth. Dragging industrial machinery across these habitats for mineral extraction could eliminate life forms before they are ever recorded, wiping away entire chapters of Earth's history without a trace. The question remains unresolved. If exploration is funded through exploitation, can it truly be called exploration at all? Some optimism lies in cooperative scientific efforts, where countries and institutions openly share information and work collectively. Global initiatives already use networks of sensors, drifting floats, and autonomous vehicles to observe ocean currents and monitor climate patterns. Expanding these systems with more advanced technologies could offer a more complete understanding of ocean processes without prioritizing profit over preservation. One day, swarms of AI-guided submersibles might serve not commercial interests, but humanity as a whole, operating as explorers whose only mission is to chart the unknown in the name of knowledge. Even so, the sheer scale of the ocean casts uncertainty over all such hopes. Even if fleets of machines roam its depths, even if every industrial project supports scientific research as a secondary outcome, the ocean will remain too immense, too ever-changing, and too unforgiving to be fully mastered. Future exploration may reveal more moments, more detail, and more astonishing discoveries, but the boundary of mystery will always shift further away. What lies ahead is not the certainty of a complete map, but the chance to understand just a little more. Whether that represents hope or illusion depends on whether we approach the deep as something to exploit or as something deserving respect, a realm where every discovery is a delicate gift. And as we imagine what the future might bring, the ocean continues to wait, as it always has, holding far more than any swarm of machines or network of sensors could ever uncover. A quiet question lingers behind every expedition, every design for a new submersible, every ambition to chart the last hidden regions of our planet. Should we explore everything? The urge to know is deeply human. It has carried us across deserts, over mountains, and beyond our world into space. Yet the ocean confronts us not only with challenges of size and technology, but also with a deeper philosophical test. In its dark waters, where countless forms of life have evolved unseen. Discovery and destruction are often intertwined. When we think about the unknown, it is tempting to picture it as a puzzle waiting to be solved. But the ocean is not a puzzle box. It is a living, breathing system, intricate and vulnerable. In areas untouched for millions of years, ecosystems have developed around fragile balances. Even the smallest disturbance, the glow of a camera, the scrape of a mechanical arm, or the removal of a single mineral deposit, can disrupt those balances in ways that may never be reversed. To open every door is to risk breaking what has endured in the darkness. Without us, this situation creates a profound ethical tension. On one side stands curiosity, the deep human drive to look closer, to understand, to push the limits of what we know. On the other side stands restraint, the awareness that knowledge pursued too quickly can demand a price far greater than its reward. Some scientists suggest that mystery itself acts as a kind of shield, protecting certain regions of the ocean by leaving them undisturbed. By not reaching into every corner, we reduce interference, limit exploitation, and avoid consequences we may not foresee. The real question, then, is not simply whether exploration is possible, but whether it is wise. Perspective matters here as well. We often frame exploration as conquest, as an extension of human presence into places that existed long before we did. But the ocean has no need for us. It flourishes whether we observe it or not. Its history is etched into layers of sediment. Its organisms evolve under immense pressure. Its cycles continue without pause. We are the exception, not the rule. The belief that every space must be opened and every secret uncovered may reveal more about human nature than about the ocean itself. Yet choosing not to explore is equally complex. Curiosity is not merely an impulse, it is also a practical instrument. Understanding ocean currents improves storm forecasting. Research into deep-sea microbes could lead to medicines that save lives. The discovery of new species expands our grasp of biology. These are meaningful gains, not trivial ones, and they remind us that exploration can deliver benefits as well as risks. The difficulty lies in finding balance, in seeking knowledge without damaging the very marvels we hope to understand. Philosophers of science sometimes describe a right not to know. It is the idea that mystery has its own worth, that there are places where not knowing is an expression of respect. The ocean challenges this concept more than almost any other frontier. If a trench conceals species that have never encountered light, do they benefit from our arrival? If a cave has remained sealed for thousands of years, is opening it truly an act of discovery, or is it a form of loss disguised as progress? These questions resist simple answers, yet they deepen our understanding of how humanity relates to the natural world. Perhaps the most powerful lesson the ocean teaches is humility. Despite our satellites and submarines, we remain small when measured against its scale. The unknown is not an empty space waiting to be filled, but a mirror reflecting our limitations. The choice to explore or to hold back is also a choice about what kind of species we want to be, one that consumes every mystery until nothing remains hidden, or one that allows some secrets to endure, protected in the darkness. Still, curiosity does not fade. The ocean seems to resonate with it, drawing us onward with hints of unnamed species, unmapped terrains, and untold histories. Yet, its greatest offering may lie not in what it reveals, but in what it keeps concealed, encouraging wonder without ownership, respect without intrusion, and an understanding that mystery itself is woven into the story of life on Earth. For all our advancement, for all the metal and circuitry we have sent into its depths, the ocean retains more mystery than any frontier we have encountered. We imagine conquering the seas, mapping every trench, documenting every living form. Yet the ocean will always be larger, deeper, and darker than we are. It is not merely a location on Earth, but a reminder of our limits, a reminder that some wonders will forever lie beyond our reach. It is easy to think of the ocean as familiar. We watch its surface daily, rising and falling with the tides, glowing beneath the sun, and we assume that what we see is all there is. But beneath that shimmering skin exists a realm more alien than Mars. a vast expanse where mountains higher than Everest stand unseen, where currents flow like rivers carrying the memory of ancient climates, and where creatures drift in forms and colors no artist could invent. Each time we venture into that darkness, we return with something new. Yet every discovery only expands the boundary of what remains unknown. There is humility in this, and also a quiet reassurance. The ocean reminds us that Earth still holds secrets, that even in an era of satellites and supercomputers, wonder has not been depleted. The sea preserves stories older than humanity, written into sediments and murmured through moving water. It shelters organisms that have never known daylight and protects landscapes that human eyes may never witness. It is at once a birthplace of life and an immense abyss, both a provider and a domain of silence. As we consider this journey through its depths, it becomes clear that exploration is not about domination, but about learning how to listen. Every eerie sound captured by hydrophones, every brief shimmer of bioluminescent glow, every fleeting sight of an unfamiliar creature is the ocean speaking to us in pieces. We can collect those pieces, study them, connect them into meaningful patterns, and learn from what they reveal. Yet the full story will always remain greater than everything we are able to gather. That reality is not a shortcoming, it is a gift. It means the ocean will forever have more to offer, more to reveal, more to remind us of the immense scale of life and the vastness of time itself. And so, as this journey into the depths slowly comes to an end, the ocean continues exactly as it always has, endless and unbroken. It waits in silence, holding its memories, protecting its creatures, quietly shaping the destiny of the world above. What lies beyond our grasp may never be completely understood, but it will always reach out to us, awakening the same blend of wonder, curiosity, and humility that has guided sailors, researchers, and dreamers for centuries. If you've felt carried along by this voyage, I invite you to return and join me again. Together, we can keep moving gently through the mysteries of science. A simple like, a quiet press of subscribe, helps this small space of curiosity find others who may be seeking moments of wonder in the stillness of their night. And if you feel inclined, share your thoughts in the comments. What do you imagine lingers in the depths? Which secrets of the sea feel most haunting to you? Every voice matters, just as every drop contributes to the ocean. This channel has grown into a meeting place for dreamers scattered across the globe, each of us linked by shared tides of curiosity. It is always a pleasure to see where you are listening from, and at what hour, as you drift into these stories. The sea will continue on, limitless and unknowable, and we will carry its mystery with us. For even as we imagine exploring every corner and lifting every shadow, the ocean will always be broader than our reach, deeper than our instruments, and darker than our imagination. It is, and always will be, Earth's greatest frontier.